I would like to introduce you Professor Chris Small. We know that other people are coming, but because of São Paulo traffic, and I think we could try to talk a little bit about the class anyway, Professor Chris has come from several years, since 2012, I think, to lead this class. It's a great pleasure to receive him. We have many exchanging his students to along the university, and he comes almost every 2 years, I believe. He's geophysicist, but works with reconnaissance for a long time. And he's much better if he speaks a little bit more about his journey. But anyway, we're going to be here today from 8 to 2 or 3 p.m. I believe. Then he's going to say when we should stop the bridge to take off or something. And I will give the presents to this of presents just to because of the great course. In this class, I believe today is the most important because of that we are just recording this class because some people will come today this morning, and we are going to put available this class if you would like to watch later. And there is a part of theoretical part of the course and practical part with the lab. So, Chris, I think you could explain how it's going to work today and other days. We changed a little bit because this week we are going to have 4 classes and 2 classes next week because of the holiday, because he's going to San Luis for future. So we had to, unfortunately, to change this week. Okay, and I will be here just in the beginning of the class, but I will be in my office, G1. If you need some students, you can just ask me. Isaac is here also, and Larissa, so if you need something, they are able to help us. And I believe you can. Chris, you can just, and maybe it's interesting to know where people come and to make you very comfortable because, you know, don't be worried about English, just speak like you get. Would you like to talk a little bit?
Sure. Bom dia. Tudo bem? Okay. That's as far as it goes. Sorry. Portuguese is complicated. So it might be entertaining for me to teach in Portuguese, but not very educational. So I will try to not use what we call jargon. But I may forget. So if I use a word that you're not familiar with, you don't understand, please say something. And I will frequently ask you to tell me the Portuguese word for certain words that we use in class so that I can learn and grow it myself. So, as Nisha said, the course is it's sort of a combination of basic data analysis, some statistics, some remote sensing, And the end point is to show you a method, a technique for doing spatiotemporal analysis. So if we're analyzing data that change in space and in time together. And so you may be familiar with some methods for spatial analysis, geospatial analysis, image analysis, possibly time series analysis. But the method that we'll talk about here in the very last class is a way to analyze the way maps change. So how things change in space and time together. And it's a very, very powerful tool. It's been used by oceanographers and meteorologists for about 50 years now, but isn't used very much outside of these fields yet. I think this will change now because data science is becoming a growing field, and so by learning how these techniques work, you may have an advantage. You may be learning earlier than other people in geography. So we'll talk about this method in the very last class. Everything else leads up to this to provide a foundation. So each class, in the beginning, I'll give a lecture and show slides, graphics, explaining the ideas, the basic ideas, and then we'll have a lab exercise, then we'll have a break. And then we'll have a lab exercise where you'll do an exercise on the computers using the NV software. But did we verify that it's working? Has anybody here used NV before? Okay, so NV is a professional software tool, a commercial software tool. It's used for remote sensing image analysis. And these are okay to use on the new board, yeah?
Yeah. But I think these are very.
Okay. So the name of the software is NV. It's an acronym. You know acronym? Yeah. Everything in remote sensing is an acronym, almost. So environment for visualizing images. And it's a commercial software tool. Unfortunately, it's rather expensive. But as students, you can purchase a student license for, I think it's $200 a year, which is not cheap, but if you use it, if it's useful to you, then it may be worth the price to have it on your own laptop. But the techniques that we'll be using in this class can be used anywhere. In R, Python, Google Earth Engine has many of these tools now. So I use NV because I'm used to using it. It's a professional standard in many institutions. the skills of using Envy are valuable enough that you can list it on your CV. Potential employers will be maybe interested to know that you know how to use the software. So you'll learn a little bit about the software in this class. Another reason that I use it and that it's very popular is because it can handle very large data sets easily. A lot of things, for instance, R and Python sometimes have problems with large data sets, but NP can handle them very easily. But the important thing is that the ideas are not specific to NP. So the ideas you can apply in other ways. If you have your own research projects that you're working on that you think this might be useful for, if you'd like to try some of these techniques, you can bring your data sets, and during the lab exercises, you can try applying some of the exercises, some of the methods to your data sets. And I can help you with your specific data sets if you like. And so if for the lab exercises you would rather apply the exercise to your own data, that's fine. I'm happy to help you do that. If you're interested in using these methods for your own research project, but you don't have data yet, I can help you get data. For instance, satellite image time series, I can help you find the data if you want to be able to apply this right away to your own research interests, your own research questions, and your own study areas. What else? I think we go for, so we have until at least 2. We have the room until 2 today. We have this room until 2 p.m.
I'll check it.
Okay. So I'll talk for a couple of hours, and then we can take a break, and then we can come back and begin doing the exercises. And during the exercises, I won't talk, or I won't talk very much. The exercises will have instructions and data, and you can either work by yourself, or if you want to work with a partner, work together with a partner, that's fine too. And then while you're working on the exercises, I'll just be here. If you have questions, just let me know. I'll move around the room answering questions, and also if you have questions about the lecture, if you have a question while I'm giving the lecture, just stop me right away and ask them. If you have other questions later, I can answer other questions during the lab section. Okay? Questions? On anything? No? Okay. But if you have questions at any point, just let me know. I'm happy to stop and answer questions.
Would you like to know where they come from?
Sure.
Yeah, I think it's a good idea if you talk a little bit about yourself, so you can know how to give the course. I think it's a good idea. Would you like to start?
Yes. Bom dia, meu nome é Larissa, bom, eu sou geógrafa formada e estou no momento num projeto na elaboração do Atlas Socioambiental dos Lençóis Maranhenses.
Você é oceanógrafo, é isso?
Não, geógrafa.
She's geographer and she's in the Atlas, in São Luís also, Lençóis Maranhenses. And she is a student, we're now two students.
My name is Camila. I'm an architect. I'm currently taking my master at Poly in geoprocessing, and I research the relationship between land use transitions and transportation in São Paulo.
Hi, my name is Sarah. I am a PhD student. I'm a geographer. Professor Ligia is my PhD supervisor. and I'm working on the relationship between extreme weather events and elderly mortality.
My name is Camila. I'm a geographer, and I'm studying my degree in Construction and Meteorology in the United. And my project is about eucalyptus in all tales of Brazil. Tales in all the history.
Okay.
Hey guys, I'm studying my PhD here. And I was studying techniques of machine learning applied to remote systems. Make some lab.
My name is Alessandro. I'm a PhD student in epidemiology at the Faculty of School at USP. And my project is trying to understand how cancer mortality relates to the expansion of healthcare.
Expansão de quê?
The expansion of healthcare.
Ok, healthcare.
My name is Jeremy. I'm a PhD student in the mechanical engineering. And I'm studying carbon capture and storage leakage monitoring.
Oh, nice. Yeah.
Good morning, my name is Evan. I'm from Rio de Janeiro, from the Universidade Federal of Fluminense. I'm a geographer, but I've been here in São Paulo about 5 years, and I study here in the new geography program. And my project is about urban areas topologies in Brazilian states.
My name is Edson. I take a degree in that. I'm studying with Professor Fulano. My area is Serra do Mar State Park. I'm studying changes in long temporality in Serra do Mar and the relationships between biogeography and geomorphology. Morphological change into fragmentation studies. With the period to 1986 to actuality.
My name is Yuri. I'm also a geographer, a PhD student, but I'm studying right now basically I'm studying images of flash flows in São Paulo, and professionally I work with stream processing applied to water treatment.
My name is Aula. I am a forest engineer, and I am a PhD student at School of Economics. And my work is also a manager and approach to systematization.
Myself was short for today. I was in other the other was in the cartography laboratory. So I was there waiting again. So I'm here. I'm changing from the program. I was from the human geography. And now I'm starting physical geography. I study biocultural diversity. That is the relation between biodiversity and cultural diversity, and in the area in the south, central east of Brazil.
So he is a student, right?
Yeah, PhD.
PhD.
My English is
Swahili. Okay. Thank you very much.
So I infer from your descriptions that not everybody is necessarily working with image time series. So the methods that we're talking about, the spatiotemporal methods, we'll apply these to image time series, but they can be applied to regular time series also. In fact, most people who use these methods aren't using images. they're using a typical application for a meteorologist might be taking time series of atmospheric temperature or humidity at different locations at weather stations. And so they have a number of measurements that are frequent in time, but not dense in space. And this is actually the type of measurements that these methods were designed for. So if your project involves maybe using a few images, but say time series of temperature or precipitation or some other variable, then you can still use these methods. It works exactly the same way. I think it's a little easier sometimes to understand when you see it applied to image time series, because the spatial picture is more complete. But the ideas apply to individual point time series as well. So today we'll just be talking a little bit about some very basic ideas that are important for everything else we're going to talk about. So today might be a review for you. You may have seen some or maybe all of these ideas before, but I think it's important to start at the base, so that in case anybody hasn't seen, or maybe you saw it years ago and have forgotten. So if you start at the same level, this may be a review for everyone. The lab exercise today is just a tutorial to teach you how the basic functions of the software, how the software works. And so the tutorial is developed by the software developers. It's not specific to this class. It really just is intended to teach you how to open files, how to extract information from files, how to display the images, how to change the appearance of the images. And so you can if you don't finish it today, you can finish it on your own anytime you like. It's not specific to this class. But I'll be here today, so when you're first getting started, I can answer questions. And I will say a little bit at the beginning of the lab section. I will explain a little bit about how the NV software stores and accesses images, so that you understand what the software is doing a little bit. But that won't take very long. And then the rest of the time you can work on your own or together, just going through the exercise to see how the software works. And then starting tomorrow, the exercises will be more specific to this class. They'll be exercises that I made up. Okay? Good. All right. Can you all see this okay? Most of my slides will have black letters on a gray background. So is it better with the lights off or on? However you prefer. All right, so today we'll be talking about the idea of how we think about processes that change in space and time together. And throughout the course, we'll be talking about both natural processes and anthropogenic, human-driven processes. And so in every class, we'll talk a bit about mathematical tools and ways to represent processes with numbers, and ways to manipulate the numbers using basic mathematical tools. And then we'll have a break for lunch, and then, as I said earlier, we'll work through the exercise. So, one way to think about this process, the way that we represent processes with numbers is through the concept of sampling and measurement. And so there are some words that I'll use frequently, and you've certainly heard many times before. And you'll see these things pop up occasionally. This tool, the reason this happens is I'm running something called an application firewall. And unlike a normal firewall, the application firewall pays attention to what's going out of your computer. Normal firewall pays attention to what's coming in. This pays attention to what's going out. So if you don't use one of these and you care about security, you might consider using one. It's very interesting which applications are trying to communicate outward at what times. This makes sense, right? An updater, a software updater, is a reasonable thing to have running. But I don't want it to keep interrupting me this morning, so I'm going to deny it. But you may find there are other applications that are trying to communicate outward that doesn't quite make sense. Or as we say, applications that are trying to phone home, to send information back to the mothership. Okay, I digress. So, a lot of people use these two words interchangeably, as if they meant the same thing. There's an important distinction between accuracy and precision. And an intuitive way to think about this, accuracy is how close a measurement is to the true value. And the true value is it may not be possible to know the true value of something. So we try to measure it, but because measurements are imperfect, we always have to remember that the measurement that we make of something may not be exactly the same. And so the accuracy tells how close the measured value is to the true value. The precision is one way to think of it is if you were to measure it, make the measurement of the same process over and over again, and it didn't change, how similar are the measurements? And so they both tell you something about the process, but they also tell you something about the measurement itself, the way you're trying to make the measurement. For instance, if you think about a thermometer, you have inexpensive thermometers. Maybe you probably have a thermometer in your phone that tells you the air temperature. But if you go online and you look at a scientific equipment company, you'll see that there are many different types of thermometers that vary in price. Price can be very different. And usually what you're paying for when you pay for a more expensive thermometer is a thermometer that is both more accurate, meaning it can get closer to the true temperature, but also often more precise, that it can measure the temperature more accurately to a smaller increment. So one way to think about this is if you were to make many measurements of the same quantity, let's say temperature, and they're not all the same. Every time you make a measurement, it might be exactly the same as one of the other measurements, or it may be slightly different. And so the accuracy, if you make a histogram of all the measurements you made, the accuracy is overall how far is this distribution from the true value. And precision is related to how much these measurements vary. Now, what you hope is that the mean value of this distribution is going to be centered around the true value. You would hope that this would be over here. But that's not always the case, depending on what type of measurement. And there's always going to be some variability here, because it's the nature of measurement devices. Almost always, there'll be some slight variation from one measurement to the next. And so part of the task is to understand whether these small differences are related to the measurement process or the actual physical process that you're trying to measure. Okay, the concept of error is a little simpler. Error is just the difference between the computed or estimated or measured value and the true value. And where it becomes a little complicated is that we generally never really know what the true value is. We try to measure it to try and understand what it might be, but we never really know for sure. But if we make many measurements, and they're all very similar, this distribution is very narrow, then we at least hope that we're getting a good estimation of what the true value is. And the bias is a systematic difference between the measurement or the estimate and the true value. So this is also the bias. So the larger the bias, the lower the accuracy. So if your measurements have a large bias, it means they're further from the true value and the accuracy is less. So really I should have, this suggests that the larger this value is, the greater the accuracy. That's backwards. This should really say bias, but it's related to the accuracy. So the larger the bias, the lower the accuracy. Questions? Oh, and Alicia is going to put all of these graphics on a shared drive for you to access, and she'll send you an email, I think later today. And so you'll have all of these slides. Okay. Thank God that's out of the way. That's the most boring part of the whole course. But we have to get it out there in the beginning. And so now we'll talk about something a little more interesting. Or we'll talk about the same idea, but in a more interesting way. So a simple question: temperature, air temperature. Say, what's the temperature in New York City? Well, it's not a very specific question, right? Because you can interpret that question many different ways. So this is a view that I took out of an airplane of just part of New York City. This is looking south along the island of Manhattan. So this is the Central Park here. Some taller buildings. Two areas with taller buildings. We call this Midtown and then the Financial District. The East River, the Hudson River, and there's your basic geography of New York City. By North American standards, New York has a lot of tall buildings. By Brazilian standards, we have almost no tall buildings. Very different layouts in our city than we do. But you certainly noticed, you go around different parts of Sao Paulo, on the same day, nearly the same time, the same day. The temperature varies a lot, right? Depending on what part of town you're in, maybe the elevation and what the wind field is like. Certainly it's with the time of day, obviously, right? And so, does it really make sense to give one number for the air temperature in New York City? I mean, how often is one number going to be representative? Sometimes maybe, but this is especially in New York because when the National Weather Service reports the temperature in New York, you know where that temperature is measured? Measured right there. In the most heavily forested part of Central Park, on top of a hill. And so it's measured at a higher elevation than the rest of the city, and it's completely surrounded by trees. And so when I see the temperature in Central Park, I know, okay, if I'm not going to be in Central Park, the temperature is low, right? Where I'm going to be today, the temperature may be several degrees higher than it is in Central Park. And so that's you can think of that as a form of bias in the temperature measurement. But representing the temperature field over an area that's complex with one number is also maybe not very informative. It's useful sometimes because the temperature changes over the course of the day, and it changes from day to day. And so knowing the temperature at 10 in the morning may give you an idea relative to later in the day or relative to yesterday what the temperature is like. But we know not to treat it as an exact number, right? Because it's going to change in space and in time. And so we automatically adjust for this form of bias and the limited accuracy of measurements. In our minds, we already do this, right? When we hear an air temperature measurement, we know how to think of it. We accommodate these types of uncertainty. So if you're visiting New York and you haven't been there before, and you're wondering, well, what kind of clothes should I bring? You might go online and find something like this. And so this is more informative, right? Because it tells you something about the seasonal variation and the daily variation together. But there's something suspicious about this plot. See anything suspicious about it? Okay, when I say suspicious, you know what suspicious means. When I say suspicious, I mean in a scientific sense. Because it claims to represent reality, but if you work with actual measurements, these curves look awfully smooth, don't they? They look just a little too perfect, right? It's kind of like the way you would draw something if you were going to draw an idealized. And you notice that it doesn't change. The daily highs and lows stay the same over the whole year. That doesn't make sense, does it? And the green background is the US average. What does that mean? Maybe it's the average of the average or the average of the daily highs and lows, but even that looks just a little too smooth, right? Maybe a lot too smooth. And so when we look at things like this, we know that. We know how to interpret that, right? We know, don't take this literally. Or as they say on maps, not for navigation, right? Did the maps in Brazil say this? In the US, when you make a map, you have legally, you're expected to put that on there. You know why? Lawyers, that's why. We have too many lawyers in North America, way too many. And so people put, it's called the disclaimer. People put the disclaimer on the map in case somebody takes their, map of biodiversity and tries to navigate ship with it. And then, runs aground and then says, it tries to sue you because, well, your map said the coastline was here. You get the idea. So we know how to interpret this. You already understand the concepts of accuracy and precision and measurement. And you know when you look at something like this, it's just there to give you a general idea. So now here's a more specific map. These are based on actual measurements at specific locations. The color bar tells you how to interpret the colors here in terms of temperature. It might look like temperatures that would be almost enough to boil water. This is because of the old system of temperature measurement we use in the US. We use the Fahrenheit scale. It's kind of embarrassing to have to look at this. Even the Germans don't use it anymore. They invented it. Okay, so now when you look at this map, right? Obviously, these are locations where there are meteorological stations or thermometers. And so if we interpret these as being precise to the degree that you can match the color of a symbol to an exact color on the color bar, you can only really see approximately, right? You can't tell me, or I can't tell you, can't tell each other how exactly what that temperature is to the nearest degree, right? Because we just don't have enough detail on the color bar, and it's hard to transpose colors that way. But you can see a general pattern, right? And even if you can't see the temperature in between the points, you can draw some conclusions from this map. And there are some suspicious things. When you see points very close together in very different colors, that's may make you wonder whether or not the measurement was really accurate, whether it was representative, or, as is often the case with air temperature, it can change over a very small distance. Depending, maybe one sensor is in the sun, maybe one sensor is in an area surrounded by a pavement that's emitting a lot of heat. And so what you don't know is the exact location of each of these sensors and how much the area immediately surrounding the sensor is impacting the temperature. And so we can look at this snapshot at one point in time. Okay, so this was 9th of June 2011, 1:15 p.m. I'm inferring p.m. because these temperatures are too high for nighttime temperatures. If it was 80 degrees at 1:15 in the morning, there would be riots. It's just too hot. But now, at 1:30, the map will probably look similar, but not exactly the same. And so, one of the things that we're going to talk about is how to interpret these types of changes. Whether the data are collected in images by satellites, or whether we're taking point measurements like this and doing interpolation, and estimating the values in between the measurements in space. And then once we have a whole time series of these maps, how do we separate the spatial change from the temporal change? Or, put it another way, how do we interpret the change in space and the change in time together in terms of a process or processes. Clear? Okay, now real data. These are air temperatures, filing in the correct units, or the preferred units, I should say, at the National Weather Service station in Central Park, surrounded by the forest on top of the hill. For the years between 1980 and 2017, these are 15-minute measurements made every 15 minutes. And each one pointed as plotted as a single point. And now we can see this gives us a lot more information than the previous graphic, right? We start to be able to see how much what the time scale of variability is. Let's see what's going on here, please.
Something wrong.
Something's very wrong, right? If these measurements are not accurate, then there's something wrong with the instrument. If these measurements are accurate, then there's something wrong with reality. I always assume when I see something like that it's a problem with the instrument. That at that point in time, it didn't make a measurement. This used to be very common when there were missing data for people to just record zeros. That's a problem if the instrument can actually have the zero value. If zero is a legitimate value, then you're introducing real error. If data are missing, it's better to use some kind of flag or what we call a dummy value, usually negative 999, something like that. That wasn't always the case, and so little things like that can be a huge problem. If you're trying to write code to analyze the data, and the bad values are put in using legitimate, a number that actually means something, then these can affect your average, for instance. They can affect your statistics. Okay, more interestingly, all right. So we see the basic pattern of warming and cooling over the course of the year. It's many years, and so we get an idea of interannual variability by looking at the range of measurement values for the same day, although we don't know the times of the day here, right? So if you look at the same day, you see a range of temperatures. Part of that could be the diurnal change, day to night, but part of it can also be the year-to-year change. So a more informative map would show not only day of year, but a specific time of day, and then for all the years. So if it was 1:15 in the afternoon, every day of the year for 37 years, then that would tell you something about interannual variability. If it was just 1 year, then each day would be the diurnal variation. So that would show you the diurnal variation on that day within that year. So what I've done here is I've taken a set of weather stations. These weather stations were set up as part of the New York City Community Air Survey, which the New York City Department of Environmental Protection did a study to look at to measure and understand air quality in New York. And so the way they did this study was they had 150 sampling stations, which were a little meteorological station or a met station, small set of instruments that measured air temperature, relative humidity, Don't think they measured ambient light level. Air temperature and relative humidity for sure. Every 15 minutes. And then there were air quality samplers. There were devices that would try to estimate the amount of particulate matter in the air. And so they put all these instruments together in a small package, and they mounted them on streetlights, on the posts for streetlights. And they had a telemetry system where each package would send via the cellular network. It would stream its data back to a receiver. And they made these measurements every 15 minutes over the course of 3 years. And they did this, the objective of the study was to understand how air quality changes in space and in time. And what some of they had other stations that measured, they collected air on filters, and then they would do a chemical analysis of the filter to see what kind of nasty things were in the air. But with these stations, with these 150 stations, they moved the stations at different times of the year. And this was recommended by the statisticians to move the stations to get better coverage. But what that means is that you don't have the same coverage in time for each location in space. Right? For one location in space, you have a lot of information for a couple months, and then that sensor package moves. And so this creates a real problem for what we call sampling, which we'll come back and talk about sampling in a few minutes. But fortunately, what they did do was for each borough, so the New York City is divided into 5 boroughs. They're larger than neighborhoods. I don't know if there's. Yeah. So you may have heard of some of the names of the boroughs. I'm trying to think of a geographic subdivision of São Paulo municipality that might be similar. Right?
I think districts.
Districts? How many districts in São Paulo?
We have
96.
96.
Yeah, it's the biggest division in São Paulo.
No, the biggest is region north, south, east, central, west.
Okay.
That is more.
But we have the
smaller, but
that's the prefeitura também.
Okay, so you have different levels of subdivisions. But it sounds like your north, south, east, west, and central is probably the closest. Even though São Paulo is a much larger city than New York in terms of its administrative. Our divisions are based on historical in the fact that New York City is mostly islands. New York's mostly composed of islands, and so there's a natural geographic division to it, but also a historical administrative division. And so BX stands for the Bronx. That's the only part of New York City that's on the mainland continent of North America. The rest are islands. Staten Island is an island. Manhattan is an island. Queens and Bronx are both at the western end of Long Island, so a much larger island that extends out of New York City. And these are from base stations. These are for each borough. There was a base station that didn't move. It stayed in the same place for the entire experiment. And so these are much easier to interpret because the entire time series is one place. We don't have any spatial movement. And so what you see here are what I call calendar plots for each base, one base station for each of the 5 boroughs, and for 2 years, 2009, 2010. And the horizontal axis is the day of the year, and the vertical axis is runs from 0 to 96, and so that is every 15 minutes, 24 hours, 4 measurements per hour. So the day goes from midnight at the top until 11:45 at the bottom, and from January 1st to December 31st. The lighter shades are higher temperatures. Okay. My mistake here. What mistake did I make? What's wrong with this figure? What information is missing? Yeah. What do the shades mean? What do the shades of gray mean? I didn't give you a scale, right? -10. So now, I certainly would have chosen a scale to encompass the normal range of temperatures we expect within a year within the city. Unfortunately, the temperature in New York goes below 0. Not frequently, but more frequently than we would prefer. Something that you don't experience that here, do you? The temperature never goes to freezing in Sao Paulo, right? Anywhere in Brazil?
South.
First south?
Yeah.
Okay. Anybody from Rio Grande? No? Are you all from Sao Paulo? No, one person's from Rio, right? So you can tell, I grew up in a place even colder than New York. And you can tell when the temperature gets close to 0. You can, as soon as you breathe in, you can tell. The discomfort level goes up considerably when you get close to freezing. Why would that be? Yeah, well, and if it's humid, it's much worse. You really feel it if it's humid, right? But you know, we're what, 86% water or something like that. And when it gets close to the freezing point, you know, it cells feel it. So I think that I probably did something like -10 to 100. Unfortunately, the temperature goes, no wait, not 100, that'd be 100 Fahrenheit. I think this was probably -10 to 40 C. It goes above 40 sometimes, but not very often. So there for your mental calibration. Black will be about -10, white will be about 40. Now, what happened here? We hope so, right? I mean, if you were just looking at one of these, you could have thought, well, this is really bad cold spell. But it's not exactly the same place. So. Yeah, so those are missing data. There was something was wrong with the instrument where it just wasn't recording for, in this case, several days. This one. And so when you look at this, you just have to ignore this. You know, like with your eye brain, just don't pay attention to it. So now there's a lot of information here. But if you take a minute and look, you can compare years for the same location by looking left or right, or you can compare geographic differences going down in one year versus the other. So we can see right away that was a bad week. Right, we see our clearly higher, consistently higher temperatures, especially during the daytime, for what? Several days at least, probably about a week. That's late July, early August. And it's consistent. You see that it's consistent across geography. This one, I remember this one actually. This was early in the year and was unseasonably warm, but not hot enough to be really, especially because This is sort of late April, early May, when things are starting to become comfortable again. And so it wouldn't be hot enough to be uncomfortable. It would be warm enough to be, maybe that's when people would start going to shorts for the first time. But back in here, when it gets warmer there, it's usually bad news, because usually this high heat in the summer is accompanied by high humidity, which makes everything worse. But it looks like it's warmer here than it does there, doesn't it? Idea why? It's not. I can tell you it was not warmer this week than that week.
This is an outlier, so I don't know optical illusion.
Sorry, I didn't hear you.
I have an optical illusion. Because
Yeah.
of the scale.
Exactly right. Optical illusion. This appears brighter because it's surrounded by, instead it's darker bands on either side of it. And so it's relatively brighter than the weeks before and after. Whereas this, the whole thing is bright out here. Or here, that appears darker. That's unusually dark, unusually low temperatures following. And so yeah, that's just your eye brain playing a trick on you. And so these kinds of things can be useful graphical tools, but in cases like that, you have to be aware that the way your eye brain processes shades of gray can lead you to believe that might have been as warm as that. In which case, you just go look at the numbers, right? So you can see we had a cold snap here. Notice that low temperatures last longer late at night, early in the morning, but they persist into the middle of the day. So people would notice that for sure. And that's late enough in the year that, like, this is probably the first time people really put on jackets that year. So this is one way to represent spatial and temporal processes of air temperature together. And for some uses, this is a convenient way to look at it, but for others not. But remember, these measurements these are point measurements. And there aren't enough stations. There are only 150 stations for all of New York City. And so it wouldn't probably make sense to interpolate and try to make maps of those point locations, because the spatial variation is probably too great. And so we could use the spatiotemporal analysis as a way of analyzing these data in a more objective way that doesn't depend on our eye-brain system as much. Okay, so here's another way of looking at the same thing, or a subset of the same thing. Here are the same, well, in this case, it's only 3 of the stations. Time series, temperatures at noon over the entire year, 2010. You see there are some of the missing data. And so now what you can see, when you look at this, you see, of course, the annual cycle, but you also see these shorter term fluctuations. And I don't know much about how the weather systems work in this part of Brazil, because I've only ever been here for a couple of weeks at a time. And to me, it seems like the weather is always the same here compared to New York. I know it's not the case, but because I'm only here, okay, this is a good example. I don't have a good sample, right? Because I come at the same time. I only come, every other year or something for a few years. And I'm only here for 2 weeks. And so my sampling, my perception of the weather here is biased because I don't have a representative sample. So in most of North America, our weather systems are dominated by the movements of frontal systems, by air masses that move back and forth, and the boundaries between the air masses, are called fronts. And so fronts usually move, in North America, they usually move at maybe 50 to 100 kilometers per hour. So you feel it when they move, especially if there's a large difference in temperature. If you have a very cold air mass next to a very warm air mass, when the front moves across the location, you really feel it. But I don't know if the fronts are as dominant in the tropics as they are in the temperate latitudes. Do you have frontal air mass? Do you have frontal systems here?
Yeah, about 70% of our rain is produced by fronts. And usually we have fronts here in the southwest of Brazil. They reach about 200 kilometers wide. So they are very, very cold for the magnetic control. Well, I think in that way, it's versatile.
But you notice it more in terms of the precipitation or the temperature or both?
Both, especially in different gradients of atmospheric pressure. It's really great when frontal system pressure, especially the pressure, goes down. So
always goes down?
What?
The pressure always goes down?
Yeah, almost always.
Okay, so that's a piece of information, right? Because that suggests that you consistently have low pressure systems displacing high pressure systems, right? In New York, it's different. In New York, it goes back and forth. We have high pressure displacing low pressure in both ways. And usually when low pressure comes in, we get a lot of rain. When we have high pressure that doesn't move for a long time, that's pretty much only happens in the summer. And that's bad news. That's like that. When you get a high pressure system, usually it's hot, humid air that doesn't move, and then it becomes very uncomfortable. But then when the cold front comes, everybody knows it, because the temperature drops very quickly, and you have cool, dry air, and suddenly everybody's happy again. Now seriously, like the entire mood of the entire city changes. If you have several days of high pressure, high temperature, high humidity, and then it breaks, it's like when you have a fever, and the fever breaks, and finally, right, you stop sweating. And so that's what's driving this pattern here, is the movement of air masses back and forth, and fronts moving through the area. Sometimes with storms, sometimes no storm, but noticeable differences in temperature. So this is why we're back to Fahrenheit again. This is why you see 30, 40 degree temperature swings pretty quickly in some cases. And so you see what the atmosphere is doing overall over the course of the year, but you also see some geographic variability, because even though the curves are similar, they're not exactly the same. And so you see, for instance, on this day, it really mattered what neighborhood you were in terms of the peak temperature. Also, notice the lows don't vary as much as the highs do. The low temperatures are more consistent across the 3 different locations than the high temperatures are. So what might you infer from that? So what determines, so what time of day is coldest? Almost always.
4, 3, 3.
Yeah, just before sunrise, right? Things that the surface is had all night to cool off. And then the sun comes up, and then what happens? They start heating up, right? Energy starts pouring in, and things start heating up. And so the system is relaxing at night as the land surface radiates the energy that it's been absorbing all day long. Then during the day, the illumination is coming in. And the temperatures, this is at noon. So even by noon, it's not even the hottest part of the day, but it's when the maximum amount of solar insolation is coming in, more or less. We forget about clouds. And so why would the temperature difference among locations be greater at noon than at 5 in the morning, 3 in the morning?
Due to the land cover,
Can you elaborate?
or trees or vegetation.
So why? Why would that change? Cause it's change? Different.
When it's trees, warm, it's trees absorb, and when it's communication, it reflects.
Mm-hmm.
Warm.
It's even a little bit more complicated than that. But yeah, that's the general idea. I was expecting an even simpler answer, but since you went into detail, I'll elaborate a little bit. So with trees, if you look at, actually let me wait until we talk about reflectance or remote sensing, and we'll come back to the difference. Basically, part of what it comes down to, what you were talking about, is evapotranspiration, and what happens when the incoming solar energy is absorbed or reflected by the different materials. And so overall, it depends on what wavelengths of light are absorbed and which ones are reflected, and then what happens to the energy that's absorbed, whether it's dissipated right away or whether it's stored and released later. But yeah, basically what it comes down to, exactly right, is land cover. Different land covers and different configurations that affect the illumination. Like for instance, tall buildings cast shadows. That has an effect. Some areas deeper in canyons, where there are more tall buildings on all sides, get little or no direct illumination from the sun. That makes a big difference. And so it depends on where these instruments were located. So this is an example that these temperatures are probably more accurate late at night, because it's not as location dependent. Whereas during the day, the temperature varies more with the location, but the location is impacted by the land cover. The temperature is depending where the sensor is located. And so if the objective was to measure the air temperature, then that shouldn't be happening, should it? And so it turns out that this is a problem with the way this experiment was designed. Because the objective was really to measure air quality. And they just included the temperature and the humidity sensors in the package for background information. Many of these packages, these sensor packages, were put in places where they're in the sun part of the day, but maybe in the shade another part of the day. And so the packages themselves, the instruments themselves, can heat up if they're in the sun, because they didn't have sunshades on them. And so this was a design flaw in the way the experiment was designed, if the intention really was to make accurate air temperature measurements. So that's an important thing to know if you're going to use these data to try and draw conclusions about changes in the air temperature. That they're very sensitive to the location. And so you would, at very least, you want to know exactly the location of each sensor and how much it was in the sun, things like that. So here is the same data. Here are the same data for over the course of one day, every 15 minutes for 24 hours. And you can see pretty consistently higher temperatures for the location in the Bronx. And fairly consistently, well, the Manhattan and Queens sent packages trade off. But now, what's going on here and here? The sudden drops in temperature that aren't happening in the Bronx.
Maybe the angle of this god into a building is kind of putting a shade on it.
Yeah, in both cases, the temperature drops by at least 5 degrees very quickly. And then it stays, in both cases, it stays low, and then it drops again. So, yeah, almost certainly has something to do with solar illumination, right? The air temperature itself shouldn't drop that fast, especially if it's not happening. If it happened in all 3 places at the same time, maybe. But no, so these are biases. These are the type of bias in the measurement. It doesn't mean that the actual measurement is wrong. It just means that it's not necessarily measuring what you think it's measuring. And this is the kind of thing that nobody likes to talk about, especially not the people who design the experiment, right? Because it prevents you from interpreting the measurements in the way that you would like to be able to interpret them, right? You hope the measurements are going to they're going to tell you about air temperature, but clearly here they're telling you about illumination as well. Or very likely, right? So it's a hypothesis. Hypothesis is in both of these cases there was some shading that caused the temperature of the sensor package to go down. Then you notice at the end of the day, when the sun shuts off, those temperatures all start to come together again. And same thing. All night long, they're pretty close together. And then they stay fairly close together until about noon. And so part of this may also be to do with shadowing. Or maybe they all had clear views to the east when the sun was coming up. And so maybe they were all being illuminated the same way. And it wasn't until later in the day that the temperatures started to diverge. Questions, anyone? Okay, here's another way of looking at the same thing. These are the reference stations again, all 5 of the stations that didn't move. This is 2 years worth of observations. And what I'm plotting here is what I call the base temperature of the base station, and then a check temperature where I plotted the base station against one of the other stations, one of these stations that moves around. And so for each of the 5 boroughs, I'm comparing the temperature of the station that didn't move with the temperature of the station that did, or a station that did. And you can see that overall, the temperatures agree reasonably well, meaning for each particular day and time, they plot close to the 1-to-1 line. If there was perfect agreement, all the points would fall on the line where they have the same temperature at both times, for both stations. But you can see there's some variability. Or what we often call this spread around the central value, we often call that the dispersion. When you measures of variability like variance or standard deviation, what you're really measuring is the dispersion of the distribution, or the dispersion of the process that generates the distribution of points. And so, for instance, we can see that the Brooklyn station has the best agreement, or the Brooklyn stations, because there are 2 stations, have the best agreement because there's the least amount of dispersion of the cyan-colored points. They fall closest to the 1-to-1 line, although sometimes they go off. And Bronx station, it looks like pretty clearly has the greatest dispersion. There are more outliers in the high and low end for those 2 Bronx stations. And in each case, we see this kind of thing happening. So statistically, this tells you something about at least the relationships between the base stations and the moving, at least one of the moving stations for each of the boroughs. What it doesn't tell you is whether or not the difference between the base station and the moving station is representative of that borough. It looks like there are consistent differences, but there are many moving stations for each borough. So really, it's only telling us about the relationship of the check station against the base station for that borough. This is a very incomplete representation of the big picture. But it illustrates the variability of the variability. It starts to get a little bit abstract, but it gives you an idea. For instance, if you were going to pick one base station, one of the moving stations and one base station, how much variability might you expect to have? Well, this shows you, based on borough, some of the differences. So there is useful information in this plot, but you kind of really have to work to get at it, right? Because you have to remember a lot of things at the same time. And so part of the point of this is to illustrate some basic concepts about measurement and interpretation of measurements and processes in space and time. But it's also intended to motivate an alternative approach to analyzing these kinds of data. A more systematic way of doing this without having to try and remember all of these things at once. And I mean, you still have to take into account things like the effect of shading on the sensors. But what we really like to do with data like this is to be able to understand the spatial changes and the temporal changes together at the same time. And that's the focus of what we'll be working toward in this class. That doesn't mean that everything, there'll still be things you'll have to keep in mind, but it can drastically simplify the process of interpreting these kinds of measurements. Okay, back to maps. Is this legible from where you're sitting? I'm sure the bottom line is, but the rest of this, can you read that? Not yet. Okay. All right. So part of the problem with some of these slides is I make these slides on a Mac with a 110 dot per inch resolution screen. And so they like, this is perfectly legible on my screen, but you never know what kind of projector, right? And if the VGA projector, and so it's always a surprise, right? How legible the text is, whether the colors are going to look the same or not. The last time I taught this class 2 years ago here, I don't know if it was the same projector, but there was a problem with the projector where 2 of the colors were reversed somehow. And so you still saw 3 colors, and I didn't notice it right away. But then I started to see the looks on people's faces, and something's wrong. And then when I turned around and looked at the screen, but this is what this image is supposed to look like. So what you're looking at here is a composite of satellite images of New York City, collected on June 1st, 2014. This is our backward state convention. This goes with our Fahrenheit temperature scale and our inches and miles distance scales. And the sensor images in different wavelengths. And we'll talk more about this tomorrow. We'll have a whirlwind review of remote sensing tomorrow, and I'll get into all of this in more detail. So this was collected by the operational land imager instrument on Landsat 8. Actually, these two channels were collected by the, we call it Aula, O-L-I, operational land imager. And it measures the reflected sunlight that's reflected from the Earth's surface. There's another instrument on the same satellite called TIR, Thermal Infrared Radiometer, and it measures the emitted radiance. We'll talk about the difference tomorrow. But the way to think about this is the red channel of this image is emitted temperature. So it's the surface temperature, basically. It's proportional to the surface temperature. The near infrared is mainly showing you vegetation abundance, because vegetation is more reflective at near infrared wavelengths. And the visible is actually visible green, but it doesn't really matter because the three visible channels of the instrument measure almost the same thing. And so combining visible reflected light with near infrared reflected light with the surface temperature tells us about land cover. This is effectively instantaneous. This image probably took about 12 seconds to collect as it was imaged, as the sensor was scanning from north to south. And again, I was bad. I didn't put the color scales on here, so you don't know the range of surface temperatures or radiances. But the point here is to illustrate relative difference. And so places where it's more red means that the surface temperature was relatively high compared to all the other surface temperatures. And near infrared and visible were relatively dark compared to the other near infrared and visible areas. And this analysis is true of the near infrared and visible. So if we look at the water areas, they're mainly blue and black. If they're black, that means they're very low in all three. So they're cold and dark. But mostly you see blue. And so what that means is that relative to everything else, it's cold, and it has very low near infrared. And that's because water absorbs infrared light. And so it's more reflective in the visible. But it varies, it changes. You see patterns. You have differences in how much visible light is being reflected. Any idea what causes those differences? In most places that would be true. Here, most of these areas, okay, that's true here. That's true here in Jamaica Bay, for sure. But most of these places out here, the water is deep enough that the light's not reaching the bottom. But what else besides depth?
Pollution.
Okay, more generally. Pollution would include sediments. Yeah, so in general, we can lump pollution and sediments and biological activity like algae and plankton into what we call turbidity of the water. And so the water can be turbid just means that there's things in the water that are scattering the light and scatter the light back out and prevent it from penetrating too deep. And so they can be natural things like sediment or semi-natural things like plankton. I say semi-natural because the plankton in nearshore areas is often affected by the nutrients coming in, and so you can inadvertently induce a plankton bloom by having too many nutrients in the water running off, or even just pollution. So that's telling you something about what's happening in the water. But what most people focus on when they look at this map is what's happening on the land. And you can see a few water bodies, but mostly you're seeing gradations between red, yellow, and green. Right? And the way additive color works, red and green are primary colors. Yellow is a mixture of red and green. And so really what you're seeing are areas that are hot, but not without a lot of vegetation. Areas that have a lot of vegetation and are not very hot. And then areas in between, yellow, shades of yellow and orange. Areas that have some intermediate amount of vegetation and are emitting an intermediate amount of heat. This is a snapshot. This is at one point in time. And so what you're seeing is the instantaneous response of the land surface to the incoming solar radiation. The hotter areas have less vegetation. They're absorbing and emitting more radiation. The greener areas, the vegetation is absorbing the radiation, but transpiring it away almost immediately by evaporation of water from the leaves, so that cools it. And in between, you have varying amounts of exposed absorptive surface or vegetative surface. So the first time I showed this image was 3 days after it was collected to a group of people in the mayor's office for sustainability. They have the mayor's office in New York as a sustainability task force, and we were having a meeting or they were holding a meeting, asked me to come and participate to talk about the urban heat island effect. And so they were. This was back during our previous mayor, Bloomberg. His administration was very focused on these kinds of things, on environmental issues. And so they wanted to do something about the heat island effect and the heating of the city in the summertime. And so just by coincidence, 2 days before the meeting, this image was captured. And it was the beginning of a hot spell. It was early June, but it was a little early for things to be getting hot, but it was perfectly timed for the meetings, the meeting on urban heat island. And so when I showed this image, almost everybody in the room was really surprised. You know, they immediately started whispering to each other. And any idea why? Right. In fact, so the geography here is that the border between New York, New Jersey, and New York runs down the middle of the Hudson River and over here. So this is Staten Island, it's part of New York City. This is all New Jersey. This is New York City. That's Long Island. So immediately, they'll notice that New York is actually not that hot compared to the surroundings. It's New Jersey. And so we have some sort of regional rivalries, you know, between New York and New Jersey especially. And so all these people working for the New York City government see this map and they say, well, we don't have a heat island problem. New Jersey does. And then of course somebody asks, well then why does it get so hot during heat waves? And then some other clever person says immediately, the wind must be blowing from the west. It's blowing all the heat from New Jersey over into New York. Maybe true, but remember what I said a few minutes ago, when it gets really hot in New York, it's usually because the high pressure system is sitting in one place and not moving. And so there's almost, usually when it's really hot and humid, there's no wind at all. None. Which is part of what makes it so uncomfortable and breeze. And so even though they wanted to blame New Jersey for the heat problem, the real problem isn't so much the locally generated heat. The problem is that when we have these heat waves that kill people, it's because the air masses. And air mass moves in and then doesn't move. And so that's, it's not entirely a local problem. It's just the nature of how air masses work. Now, for sure, it's still going to be more comfortable here in a heat wave than it's going to be over here. No doubt. But these areas that you see here, so this is a big shipping port. That's the Port of Lisbon. This is where the big container ships come in. They used to come in over here, now they come in over here. Some people still feel bad about that. I mean, money went from here to here. This is heavy industry, heavy industrial areas, factories, large open areas of pavement, no trees, clearly. And so no shade, lots of absorbing surfaces, area that absorbs solar radiation turned into heat. These corridors here, that's also a lot of development, like strip malls and things like that, big buildings. This is all suburbs. So these are all a lot of houses and things in here, but also a lot of trees. Same thing out here. These things are parks, the very green areas are parks. So those are mixtures of trees and grasses mostly. This park right here stands out. Notice it's a little bit, it's almost cyan colored. It's not just green, but it's sort of greenish blue. And this one right here, it's the cursor of the east here. Yeah, this one right here. A few of the others, but this one really stands out. The name of this park is Forest Park. It's not a very original name for a park, but all it is just one big patch of forest. There are no open grassy areas, it's just forest, it's all trees. And so it's even cooler because it's more vegetation transpiring in deeper shade. So this is an example of the kind of information we can get from images, especially when we combine different types of image together and use the variations in the color to interpret what physical processes are happening. And so in this case, we're using 3 different images collected at the same time, measuring 3 different things. And we're interpreting that in terms of physical processes. What we could also do is we could just take, for instance, thermal infrared images collected through time over the entire area like this, and then try and interpret the spatial and the temporal changes in the temperature at the same time. That's an example of the kind of thing we'll be doing a little later on. But I think it's important before we get into that to spend some time looking at images like this and thinking about how to interpret the physical processes that what we're going to infer from the images based on what's emitted or what's reflected. Does that make sense? Okay, so now we're going to tie those NICAS stations, meteorological stations, with the surface temperature. In this case, it's an image just like what you were looking at before, except collected by Landsat 5. And these are multiple images collected over, I forget how many images, collected, no, in this case, no, I'm wrong. That's, no, I'm right. We're looking at multiple images. I don't remember how many different dates. Even though I didn't label it, I know that it's multiple images, because look at the range of temperatures. Never have that range of temperatures. I mean, even in silly Fahrenheit degrees, we never have that range of temperatures at one time in New York. We never go from below freezing. So freezing is here at 32 Fahrenheit, and water boils at 212. 32, 212. Now you see why we use Celsius. Right? 0 to 100. So these images obviously span different dates because they see the whole range of temperatures of the year. And so what I've done is for each of these images, I took every one of these stations, these meteorological stations, and at the time of each satellite overpass, I took the temperature of the meteorological station, the air temperature, at the time that the satellite passed overhead, and the image was collected. And I extracted that air temperature, and then also extracted the surface temperature from the satellite image at that location. And so for the location of each of these stations, at the time of each of the satellite overpasses, we have an air temperature and a surface temperature. That makes sense? Here. And so what we're looking at here is the overall agreement between the surface temperature that the satellite measures and the air temperature that the met station measures. And just to make the plot more complicated, I took 3 different times of the day. The satellite only passes overhead at the same time every 16 days. And so the satellite is about 10:45 in the morning, usually, give or take. You know, as the orbit drifts, the time changes a little. So the red points should have the closest agreement. If the air temperature and the surface temperature are the same, then the red points should be the closest. And then the green and the blue are air temperatures measured later in the same day. Well, or that night. So we would expect the red to be the closest, the green furthest, and the blue, or green further and blue furthest off. And so now, when you interpret this, what can you see? What would you infer from this, from the relationship between the air and surface temperatures over the course of the year at 3 different times of the day? You see the difference in the pattern of the red versus the green versus the blue points? Does it make sense physically, what you would expect? Like generally, the blue points are mostly below the 1-to-1 line, right? So the air temperatures at 11:45 in the evening are generally lower. Not always, but generally lower than the surface temperatures earlier in the day. Whereas the air temperatures at 10:30 and 15:30 are mostly higher. Mostly a bit higher, right? They're mostly above the 1-to-1. Sometimes they're quite a bit higher. But overall, the temperatures, the air temperatures and surface temperatures over the course of the year, they form a trend. As we would hope, right? Good thing. If they didn't, then somebody's got some explaining to do. And generally, the nighttime temperatures are significantly lower, tens of degrees lower than the daytime temperatures. But the daytime temperatures are generally higher, the air temperatures are generally higher than the surface temperatures. Why? Why might that be? They're not always higher. There's plenty of red and green points below the line. But it seems like more of them are above the line, especially up here, the higher temperature end. So we're looking at summertime up here, right? The temperatures are highest. And so we can look at this and infer that the high temperatures, the higher temperatures that occur in the summertime, the air temperatures are generally higher than the surface temperatures. So there are at least two things that control the air temperature. It's the heating from the ground or cooling from the ground, depending, right? If the air temperature is higher than the ground temperature, then the air temperature will heat the ground and the ground will cool the air, or vice versa. But then, remember, we have the fronts moving back and forth. And so you can have air that was heated or cooled somewhere else moving in. And so, if we have a cold front that comes in, the cooler air might be colder than the ground surface below it, even though the ground surface below it's being heated by the sun. So it's a more complicated problem than a lot of people realize. And you guys know what I'm talking about, you're geographers, right? But the people sitting in the meeting that I just told you about were not geographers. And so, they don't think, most of them don't think about this. They don't think about the fact that, until you mention it, that, yeah, air temperature in the summertime can change 20 degrees from one day to the next. And that's not because we don't have enough trees or we have too many trees. It's because the air masses move. And yet a lot of people who think about urban heat island effects don't really think about moving air masses. And so what you're seeing here is a complicated result of the processes that are responsible for the air temperature and the processes that are responsible for surface heating. So there's a lot of information here, but you need to keep a lot of things in mind when you're thinking about it in order to interpret it. And again, we can sometimes avoid these kinds of complications by analyzing data spatially and temporally together. Okay, so now this is, yes?
So in the summer, the temperature is mainly coming, the higher temperature are coming from the air masses that were not heated near New York. Is that what you...
Sometimes. I wouldn't say mainly, I would say sometimes the high temperatures are related to the movement of air masses. So you might have air that was heated somewhere else moving in and displacing the cold air. But sometimes it is due to local heating. Now, the thing to keep in mind too is the satellite overpass is 10:45, around 10:45 in the morning. But the ground surface reaches its highest temperature from the sun at what time? Approximately. Even later, actually. Even though the maximum incoming solar is around midday, it's, later, 2, 3 so. It depends on the location. And also it depends on if there's any shading. It depends on the day of the year, but generally it's a little bit later because it's absorbing the heat, right? And so what it really comes down to is the rate that the ground surface is absorbing the heat and the rate that it's emitting it again, right? So you have heat flowing in and heat flowing out at the same time. And so it's a bit more complicated, but the net result is that the hottest time of the day in terms of emission is usually sort of mid-afternoon. But, yeah. Does that make sense? Any other questions on this? Okay. So now we'll look at something a bit more informative, or maybe easier to interpret. So this image that you're looking at here is an image collected by a thermal camera, actually pointing out the window of my apartment at an intersection. And the color scale is here, although it's probably very difficult to see the reds and the whites. The highest temperatures of the whites are, the high temperatures are up here. These are, at least they're in Celsius. So we're going from 10 degrees to 50 degrees C, and the histogram shows the temperatures relative to the color. And so this is a thermal camera that images in a way very similar to the thermal sensors on satellites. The cameras that we're used to using measure the reflected radiance, whether it's from sunlight or scattered light from the atmosphere or indoor lights, artificial lights. They measure the radiance that reflects off of surfaces at visible wavelengths that our eyes are sensitive to. So a normal camera is sensitive to the same wavelengths of light that our eyes are. A thermal camera works in the same principle. It's measuring radiance, but it's the radiance at longer wavelengths that's emitted by surfaces as heat. And so the color scale here corresponds to heat, or heat emission by different surfaces. And so again, warmer colors are higher temperatures. Some of the cyan here looks like it might be white. The only things that are white are the very edge of the window ledge here, where it's very hot, the wheels of the cars, and that's pretty much it. So for the most part, the red is the hottest, and the deep blue going to black is the coolest. And so this is an image that was captured instantaneously. This was, I think I was capturing one image per minute when I did this. And so now you can see at a much finer scale the way the different objects in the urban environment are emitting heat. And I don't remember the time this was collected, but I can infer that it's probably late morning to early afternoon. And I know that because in the summertime when I was collecting these images, the sun comes up basically over here, and then it swings around to the south. And so early in the morning, all of this is in shadow. And then later in the day when the sun's coming this way, later in the day, when the sun's coming in this way, the sun illuminates this street here and the sidewalk. It never comes in high enough to illuminate this wall. And then as it swings further to the south, the shadow moves over. And so we can see that this building face here is noticeably warmer than this one. But it's not really hot, so it's certainly not illuminated. And it probably hasn't been illuminated for a few hours because it's cooling down. The street is hotter because it's illuminated more, right? Because it's facing up. And so it receives more direct sunlight over more of the day. The deepest shadows are down in here, because this area is never directly illuminated. The sun never hits this area directly. Or the closest it ever comes is maybe parallel to that wall. So this wall is never illuminated directly, ever. And the area down in here where the wall meets the sidewalk maybe gets a few minutes of direct illumination when the sun moves across. Actually, the most information here about, if I don't remember this, I could have told you that immediately that it was early mid-afternoon, because that's when the window edge was illuminated. So, knowing that, is there anything surprising about this image? So the reason that I was collecting these images was as part of an experiment to try and understand the effect that vehicles have on the urban heat budget, the urban thermal environment. And so this is what we were after, looking at a large number of vehicles to see how much heat vehicles contribute, what types of vehicles contribute more heat, how much of that heat is being absorbed versus heating the air, how much is being absorbed by the ground versus heating the air. And so, as expected, the hood over top of the engine is hot, as it should be. People are often surprised that the wheels are so hot. Pretty much all car wheels are hot. Why?
Friction.
Friction. Two kinds of friction. Right? There's the rubber in contact with the road, that's constant friction. There's also the brakes, right? So when brakes work, they squeeze the disc. That generates an awful lot of friction. And I can tell that this is a taxi cab because it has the placard on top. It's a taxi cab with the air conditioning, with healthy air conditioning. It's very cool. The windows are very cool because the air conditioning is cranked up. Notice this in both vehicles, especially this one, it's much cooler in the front. The windows in the back are not nearly as cool. Whereas the air conditioning, the vents for the air conditioning are in the front usually. The van, I'm guessing, has been parked here for a little while. Well, that's the parking space that it's in. So its wheels are still hot, its engine is still hot, but it's starting to cool off. Trees. Let's see if one of these should be. Okay, so this point here in the tree canopy is this time series here. So this is seconds from the beginning of the, no, this is not the beginning of the day. This is mid-morning. This time series starts in mid-morning. And so you can see what happens here with the tree is it doesn't change the temperature much over the course of the day until all of a sudden it drops. In fact, all of these surfaces, so number 2 is the window here, number 1 is the air conditioner unit, above it in the window, number 3 is the street, and number 4 is the tree canopy. So, let's start with number 2. Let's see what's happening here. Temperature's fluctuating a bit. We'll talk about why it drops in just a second. What's happening with the air conditioner? This is the outside of the air conditioner we're seeing. The unit that's outside the window. Turn it on, turn it on. That's it. The compressor, this is the compressor kicking on and off. And so you're seeing every time the thermostat turns the air conditioner back on, it fires up the compressor. The compressor's outside the window. And so the compressor heats up, and then at some point it spikes. I don't know enough about how compressors work to know why it's spiking like that. The compressor runs for a while until the temperature drops inside the room. The thermostat turns the compressor off, and then it cools off for a while. The temperature in the room goes up. The thermostat kicks back on. Bang, there it comes. The compressor comes on, it heats up, cools off, runs for a little while. Notice each cycle is hot in the very beginning, and then hotter just before it shuts off. So you're seeing how the air conditioners work. Where you see the cycle of the compressor and the thermostat working together. That's anthropogenic heat. The temperature of the window just below the air conditioner is a little bit simpler. Right? It's also fluctuating, but by well, these are different scales. So, but it's fluctuating by less than 3 degrees. Because this is going about, the whole cycle here is almost 10 degrees C. And the street, this line right here where this cab is stopped, that's the line of the crosswalk. And so when cars come to this intersection, they stop here or further back. And so this is almost in the intersection, but it's where the cars stop and they're waiting for the light to change. So this is an asphalt street. This was not recently paved, and so the asphalt, you notice, asphalt starts out black, but it weathers pretty fast, right? And so as asphalt gets older, it becomes lighter in color. And so therefore it absorbs less light and reflects more light as it gets older. And eventually, very old asphalt is almost as bright as cement in some cases. So they're all doing basically the same thing. Even the air conditioners, they're warm and not, changing kind of frequently, and then they all drop at the same time. The street's maintaining about 24 degrees C, so room temperature, right? But the temperature keeps shooting up and down like that, really fast. Any idea why? Cars, right? Everybody get that? So depending where the car stops, if the car stops there, the cycle of the light's about 1.5 minutes. Car stops here, if that pixel is on the car's hood, it's hot, up goes the temperature. But if the car is a little bit further forward, and that pixel is on the windshield, then it's colder. And so we see these wild fluctuations about the mean. It has very little to do with what's happening on the street until later at night when there are fewer cars. And so the measurement at that point is telling us more about what's passing through that pixel's field of view than what's actually on the ground. And you can see it goes on, well, until pretty late. Well, there's still a little bit. The engines aren't as hot late at night. The air conditioners are about the same. And so you see this fluctuation about the mean. The mean is changing. You still see fluctuation about the mean related to this process of cars pulling into the field of view, and either the hot part of the car or the cool part of the cars. Okay, finally. All the doubt that we're waiting for. What happened here? Any idea? That's very, very fast change. It's a very fast drop in temperature over the course of a few minutes at most.
Which one was that?
Sorry?
Which one was that one?
Well, it happens in all of them. This temperature drop happens at the same time in all of them. I can't read how many seconds that is, but this drop in temperature happens at the same time for all of these, for every pixel of the image.
They related to shade and solar shading.
It's a pretty big drop in temperature. The thing is that this area is not all, it's shaded at different times, right? The illumination changes in different time periods for different faces because the surrounding building topography is kind of complicated. So later on, I'll show you an illuminated LiDAR map of this area to give you an idea. I should have showed that earlier. Okay, so wind. Yeah. Okay. So wind, if the air was cooler than the surface, then wind would cool the surface, right? But it might not cool all the surfaces equally, because depending on the direction, right, there are going to be wind shadows and things like that. Clouds, if a thick, heavy deck of clouds came in, that would cut off all the solar, and that would cause things to drop. For sure.
Rain.
So that.
It starts raining.
Why rain?
It's a lot of water.
Right.
Lakes,
So any of the processes that you mentioned could cause a cooling. Although for most of them it would be hard to imagine the cooling being so simultaneous. Certainly the illumination and the wind, I would think they would cause the cooling to be a bit more gradual, maybe different rates at different locations. But yeah, so what actually happened here was not just rain, but a line of thunderstorms came through. And so it was rain, but it was a lot of rain, very quickly, very late. Maybe not so unusual for the rain that you get here. I've been here when it rains heavily. You get your typical rainstorm would be a very big deal for us. But I'm guessing that when you have thunderstorms here, yeah? Okay, so you notice the difference between a thunderstorm and normal rain? I mean, aside from all the theatrics, is that the rain, at least in the temperate latitudes where I'm from, when we have a thunderstorm, the rain is cold. The rain that comes down is really cold. Compared to sometimes we have warm rain, lighter warm rain. But when we have thunderstorms, the rain that comes down is cold and sometimes even freezing. We have hail. Sometimes the rain's already frozen when it hits the ground. And this was a big, violent thunderstorm that came through. And so it dropped the temperature a lot because the rain was so cold. And so why would rain from thunderstorms be colder? Think about how a thunderstorm works. Thunderstorm is a form of what we call deep convection, where if you see a thunderstorm, the clouds are, they form these big columns. The clouds go really high. Yeah, so you get very deep convection cells when you have a thunderstorm. And so the water that's condensing and forming in the cloud, in many cases comes from further, higher in the atmosphere when it's colder. And so by the time it comes down, because it descends so fast, because it has such fast convection, that it doesn't really have a chance to heat up as it's coming down. And so the rain will often be really, really cold when it hits the ground. And that was the case here. What happened here was we got doused by a big thunderstorm. And in this case, in the case of the tree, it went from about 33 down to about 20 degrees, so 13-degree drop. And on the hotter surfaces, I guess none of the surfaces are really that hot. This one also was about the same. Yeah. So this is what we'd like to have for everything. What we'd like to have are images with a lot of spatial detail and a lot of temporal detail. Frequent in time and detailed in space. And we're going that direction, right? These kinds of data are becoming more and more common. These thermal cameras like this are still fairly expensive. Camera that I used to collect this was probably $40,000. But now you can get you can get a camera that can collect similar imagery, not as precise. Comparable accuracy, but not as precise. It can't measure as small a difference in temperature change, but plenty to do this for about $5,000. But it's still $5,000, right? We'd like to see them, down in the, we'd like to see thermal cameras do what normal cameras did, right? They become so cheap, they just put them in phones. So there are attachments actually you can buy that plug into smartphones, little sensors that plug into the USB port that will make thermal images, but nowhere near this detail, nowhere near this accuracy or precision. But they do make these little instruments now. I think they're on the order of a few $100s. So the price is coming down. But what we'd like to have are images, spatially detailed images with very frequent, very short time interval. And these kinds of data are where the spatiotemporal analysis tools become really valuable. Because when you have a lot of spatial detail and you have a very short temporal sampling, you can image many different types of processes at once. Whether the process of the air conditioner compressor, or the rainstorm, or the diurnal cycle. And the more different types of processes you have, the more complicated the data are to interpret. And the more complicated the data are, the more powerful the mathematical tools become. Okay, ready? Any questions on anything that we've already covered? Okay.
When you check that data from surface and air temperature from that direction? From stations and from
this?
More. Yeah, that one.
These?
No, it's from yeah, that one. No, sorry. Before that. Yeah, that one.
This?
Yeah.
Okay, this came from multiple sets of surface temperature images like this from different dates. So like the red channel of this from Landsat, from Landsat 5. Those data are available from the U.S. Geological Survey. Tomorrow I'll give you the sources for where you can get the satellite data. But the thermal data from Landsat have a spatial resolution of the older imagery going back to 1982 have a spatial resolution of 120 meters and a temporal resolution of at most every 16 days, but usually less because of cloud cover. The newer sensors from Landsat 8 has 100 meter resolution, and it's from 2013 to the present. And the temporal coverage is generally better with Landsat 8. They collect more of the. Tomorrow when we talk about satellite missions, we'll get into that in more detail. This type of data are available for free from the USGS going back to 1982. And the air temperature that they're being compared to are the same from this data set, this data set, this data set. These are all from the New York City Community Air Survey. I don't know if those data are publicly available now or not. They didn't used to be. They used to be proprietary. In fact, I had to sign an agreement to get to use them because they weren't public when I received them. The report published from this study is available, and I can. I'll give you the URL for that report. I'll dig it up tonight and I'll give it to you tomorrow in class. If you're interested in this kind of thing, like air quality surveys, it's a pretty interesting report. A lot of work went into it, a lot of information. And the report is certainly publicly available. I don't know all the data though. I'll email some people and see if the data are available yet. But as I mentioned when we were talking about this, the air temperature and humidity data are difficult to use to understand air temperature because the experimental design was not focused on measuring air temperature. And so they have this problem of heating, stations being exposed to the sun sometimes, not other times. The stations weren't shielded from direct illumination. That was the problem. And so I've never seen any study published using these air temperature data. Probably because that flaw in the experimental design introduced a bias. So that answer your question? Okay, anything else? All right, so now we're going to shift a little bit and talk about some other basic ideas related to sampling and resolution, and the limitations that we have to understand when interpreting measurements made by different types of instruments. So this is an example of the three types of resolution that we have to consider when we're using remote sensing. And so I think the most intuitive for most people is the idea of spatial resolution, and that's basically just a function of the size of the pixel and whether or not the pixels are small enough to be able to resolve the objects that you're interested in. And so when we don't have sufficient resolution for our measurements, when the resolution is not enough to accurately represent the object of the process, we call that aliasing. And I'll talk about, this word alias? It's most commonly used when somebody takes a different name. Like criminals don't want to use their real names, and so they'll take an alias. They'll impersonate somebody else. And so the alias is the made-up name that you use. And you'll see the connection in just a minute. And so when we're trying to sample a process in space or in time or in wavelength, if the sampling is not sufficient to represent the process accurately, we say that the sampling has aliased the process. It made the process appear to be something different. And so you see an example here. You see an image. How many people here recognize this building? Okay. Yes. So you're aware of where my tax dollars go. A large part of my tax dollars. And so it's recognizable because it has this unusual structure. And so even looking straight down at it, which is usually the least informative view of a building, even looking straight down is recognizable. And so this is, okay, so what you can see what's happened here is that I've aliased this figure because the resolution of the figure is not high enough for me to be able to read the caption. So that in itself is an example of aliasing. But this is, I'm guessing that this is probably a 1 to 3 meter resolution image because you can make out the separate concentric corridors. This is, I think this is 10 meter resolution and 30 meter resolution. And so what you can see is as the sensor averages the reflected light over a larger and larger area, the pixels become larger, and you start to lose critical detail. And the interpretation is more difficult because the pixels are larger and you're losing your fine detail. And finally, by the time, you might still be able to recognize it as the pentagon in this image, but certainly not in this image. Because the pixels are just too large, there's no spatial structure to recognize. Spectral resolution has to do with the range of wavelengths. And if you're not familiar with wavelengths, we'll talk about this from the beginning tomorrow. But it has to do with how narrow a range of colors an instrument can distinguish, and generally the number of different colors it can distinguish. So the most obvious example is a color photograph versus a black and white photograph. Black and white photograph only images shades of gray. Color recognizes distinct colors. And so you can still recognize a black and white image if you recognize the spatial pattern, but you don't really have the color information. And so that's, and in the case of the image we were looking at earlier, we were looking at completely different parts of the spectrum, and therefore completely independent types of information. And so the colors that we were looking at before are not the colors that you would see if you looked at the image. They're what we call false colors. By combining different parts of the spectrum together using color, we can interpret the colors even if they're not visible. And then finally, temporal resolution. We talked about this a bit already, depending on how often you make your measurement. The NICAS temperature data measured every 15 minutes are enough to show us the daily cycle easily. Because we have 9,600, 3,600 minutes. 60 times 24 minutes in a day. So 15 minutes is more than enough sampling to represent daily cycles, but not necessarily enough to capture more frequent processes. With satellites, it's more of an issue because all satellites, most satellites have revisit times of about 2 weeks. Some satellites have more frequent revisits because they have a very wide swath. But then they're seeing the same place more frequently, but from different angles. We'll talk about this tomorrow. So these are all things that you need to consider when we're interpreting data. Is there a water fountain nearby somewhere? A water fountain? This is an illustration of the idea of aliasing. And what we're about to talk about is the beginning. It's the basis of a whole discipline called information theory. And specifically a part of information theory called signal theory that was developed really beginning in the 1960s when electronic communications first first became common. But it's the basis for now a huge range of scientific questions and disciplines, because we moved to electronic measurement of everything. And so even before the current big data revolution, this process was beginning in the sciences when people began to make instruments that could make measurements automatically, and especially with digital sensors, with instruments that could capture, make electronic measurements, and store them in digital form and on computers. And so this is a fairly young field, but the ideas are pretty important to almost everything now in science. So so I'm going to present this idea in terms of time, in terms of time series, because I think for most people that's a little more intuitive. But exactly the same concept applies in space or in other dimensions like wavelength of light, of radiation. It can even be applied in more abstract cases that I'll mention later on, because the underlying mathematics doesn't change. So we have some process, and we learn about the process by sampling, by making measurements, making repeated measurements called samples. And so the sampling frequency becomes important. That is, how often do we take the samples? How often do we make a measurement? Now, in this case, I'm using time as an example, but remember, if it's in space, how often translates into how far apart. All right, so how far apart are your measurement locations? And so, in general, we refer to this as sample spacing. And in this case, to keep things simple, we'll be talking about samples made at the same spacing. So samples measured at a constant time interval or a constant spatial distance. Now, this theory also applies to samples that are not measured at uniform intervals, but it's more complicated. And it's much, much easier to understand the theory if you begin with uniform sampling. Then you understand the concepts, and then you can back up and say, okay, now what happens if the samples are not uniform? So you understand the concept first with the simple case, and then if you need to understand the more complicated case, you go backwards and you have that existing understanding to work on. So one of the central theories of sampling theory, the central ideas, has to do with something called the Nyquist frequency. The Nyquist frequency is the minimum sampling frequency necessary to resolve a feature accurately. I left out accurately. And what the sampling theorem says is that the minimum sampling frequency, or the Nyquist frequency, is twice the smallest frequency of interest of the process. Okay, so if you have things changing, like the temperature we were talking about, right? Temperature changes on an annual cycle, and it changes on a daily cycle. And if you care about shorter period, like seasonal or sub-seasonal processes, then you need to sample more frequently than if all you care about is like annual changes in temperature over many, many years, interannual changes over many, many years, then you might be able to just sample once a year. But if you care about seasonal changes, higher frequency, so 4 seasons per year or 1 cycle per year, then you need to sample more often. And so in that case, in the case of understanding seasonal changes, you would need to sample at least twice a year, generally more, but at least twice. But if you care about diurnal changes daily, then you need to sample at least twice a day. But if all you care about is decadal changes in temperature, interannual temperature, you don't need to sample frequently more than once a day necessarily. So really what this is saying is when you're designing an experiment, think about, okay, what's the shortest time period or the smallest spatial scale that I care about? And make sure that you sample enough that you represent that accurately. If you don't represent it accurately, then you get what's called aliasing. Okay? So in this case, this example here, the continuous curve will be the actual process. That will be the underlying process that we care about. So let's imagine that this is air temperature. And let's say that we know from the very beginning, we know that air temperature has a strong daily cycle. It's not exactly the same every day, but we know that there's always the heating during the day and cooling at night. And so we know that to represent that cycle, we need at least a minimum of 2 samples a day, bare minimum. And so we know that the underlying process has this 24-hour cycle. So we know we're going to have to sample at least twice every 24 hours. So I have the small dots here are just markers representing discrete points on this continuous curve. Circles, the open circles, are samples. So what happens now if the process is the continuous curve? What happens if we sample it 1, 2, 3, 4, 5, 6? 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So the open circles, there are 16 circles representing 1 cycle of the sinusoid. Right? So we're sampling it at 16 samples per cycle. So 8 times more than the minimum we need. The minimum we need is 2 samples per cycle. We're sampling it at 16 times per cycle. So now, if you just connect the open circles, the samples, if you just connect those with straight lines, this is what you get. Or actually, this is what you get. And visually, it looks the same. Because we have enough samples that if you connect them with straight lines, or if as we say, if you were to linearly interpolate between the samples, the interpolated value, if you assume straight lines, the interpolated value would be close to the real value. Almost everywhere, except down here where the thing curves a lot. So here, we call this being oversampled. We've collected more samples than we need to represent this sinusoidal shape accurately. But collecting samples aren't free. Right? There's some cost associated with making a measurement, even if it seems like it's almost nothing. There's cost associated with making a measurement. There's cost associated with storing measurement. There's cost associated with backing up the storage of the measurement. So if you think forward, if you think for your experiment, if oversampling at this rate is going to cost you 1,000 AI for storage and backup and everything. Hard drives, instruments, and then say, well, if the storage alone costs $1,000, storage and the backup, if I sample half as often, then the storage and the backup cost is cut in half. So we have some incentive to think about, how much oversampling do we really need to do? And so the question becomes, what if we take every other sample? What if we take fewer samples? In this example, every other sample, so half as many samples. Will we still represent the process accurately? And so here's what happens if you take every other of these 16 samples, connected with straight lines. In this stretch, it looks reasonably accurate. But clearly, up here on the top, where the thing is the most curvature, you're losing information, right? Because if you were to interpolate linearly, you would underestimate the temperature at these points, these areas in here. Now, you don't have to interpret linearly or interpolate linearly. There are other ways of doing it, but in order to do that, you have to make assumptions. Linear is the simplest, and so that's what we use for examples. In this example. So you can see here that the cost of lower sampling rate is that you lose information around the peaks and the troughs. And so you can ask yourself, well, can we afford to lose that information? This is inaccurate, but is it accurate enough? So when you're designing an experiment, when you're looking at the cost of sampling, you balance that against the cost of inaccuracy or bias, so introducing bias into your measurements by not sampling often. Now, if you know exactly what the process is, that's easy, right? But if you knew exactly what the process is, you don't need to be measuring. So it involves some guesswork. So now we've cut the number of samples in half, and we still have a reasonably accurate representation of this time soil process. So let's save some more money. We've cut the number of samples in half again. Now what happens? Now we lose all of this. So we lose information about the high and the low values. That, if this is temperature, that's a big problem, right? That's expensive because we often care more about the extremes than we do about the intermediate values. In fact, that's true for most processes, right? If you lose out on the extremes, that's where things can become expensive. So it still has this kind of periodic character. We can still see that it's repeating a pattern, but it's not purely sinusoidal anymore because it's not representing it the same way every time. Right? Here it's more flat, here it's got more slope to it. So now we've introduced some serious inaccuracy here by not sampling enough. Now if we go even further, look what happens. Now it's not even periodic anymore. Right? So we're missing the highs. We get the lows sometimes, but not other times. But now we don't even capture the repeating character of the process. And so what you're seeing here is the aliasing gets progressively worse. The distortion, the inaccuracy gets progressively worse, just because you're not sampling often enough. So now, what about the Nyquist theorem? Right? The Nyquist theorem. In principle, we should only have to sample it. We should only need 2 samples per cycle. Right? That's the bare minimum. But what you don't hear about is the phase of the sample. At what part of the cycle are you collecting the samples? And so, if you go by the Nyquist theorem and you say, okay, we care only about the daily pattern, only about the daily cycle. And so we're only going to collect 2 samples a day because all we really care about are the high and low temperatures. Well, if you're lucky and you start measuring at peak and the low temperature is exactly 12 hours later, then you're lucky, right? And you represent the sinusoid as a sawtooth. But you're still getting your high and low temperatures. But if you don't know where those peaks are, and you just start sampling, so you can do it, you can take a sample here, 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 here. You're still getting the daily sun, you're getting the 24-hour period, but you're consistently missing the highs and the lows. So you're sampling at the NICOS frequency, but you don't know where to start it in the phase of the cycle. If you're really unlucky, and you take your 2 samples here and here, then you're still getting the 24-hour period, but yeah, you're stuck, right? Because you're capturing almost none of the true variability. And so the key word in the sampling theorem is the minimal sampling frequency. All that means is if you go less than that, something bad is guaranteed to happen. But you generally want to go a bit more if you can afford it. But you don't necessarily need to go 16 times as high.
I imagine it also depends. I wonder if it also depends on the amount of cycles you have. It's like if you sample 3 times, but then you have the cycles in intervals of 3, that would be also a problem, right?
Yeah, and so that's why it says the smallest frequency of interest, right? And so, but what this doesn't say is that if there are higher frequencies, well, what we call higher frequencies of the process, but shorter frequencies of sampling, it depends on how much amplitude they have, how much variability. Right, like for instance, the rainstorm example. That happens very fast. So but it's a big change. It's a big change that happens very fast. And so you can miss that, but the problem is that if you capture only part of it, then even something of higher frequency, a shorter period, that you care about can corrupt your perception of something of longer period if the shorter period thing has high amplitude. Does that make sense there? I guess I should. In terms of terminology, I should mention. So the difference between the highest value and the lowest value we refer to as amplitude. And the amount of time that it takes for a pattern to repeat, we call it period. The period is just the repeat time if it's something that repeats. If it repeats, we refer to it as periodic. Even if it's not this shape, if the shape repeats, then we say periodic. So the period is the amount of time that it takes to repeat. The frequency is just 1 over the period. It's the inverse of the period. So if this period is 24 hours, then the frequency is 1 divided by 24. Or if you're thinking about sampling, you can say the sampling frequency is 24 samples per cycle. Okay, so often we talk about sampling, we simplify it, and we just talk about the number of samples per cycle, assuming that there is some kind of repeating cycle. So a lot of these ideas are based on the idea of sinusoids, of exact, perfectly replicating things with fixed periods. The ideas are developed with sinusoids, but then once you have the theory, they can be generalized. They can be the same idea can be applied to things that don't repeat, which seems almost too good to be true, right? That you can start with an assumption of something simple, develop a theory for it, and then apply it to something more complicated. But it's true, it works. It actually works really well. Okay, questions on any of that? That's as complicated as it gets. That once you understand this, everything else is relatively simple. But if it's your first time seeing it or you've never thought about it this way, it may take you a little bit of time to think about it. If you like, I could pull some, I could find some examples, say like YouTube videos or documents that explain this stuff in a little more detail, if that would be helpful. Because I know when I was a student, I almost never got things the first time in class. I always had to go back and absorb it later. So if having some additional supplementary examples, and I find that there are a lot of really good videos on YouTube that illustrate it with dynamic examples. So if that would be of interest, I can dig up some examples for this stuff online. Okay, so some examples of aliasing. In this case, these examples are to do with images because I teach a remote sensing class, and so I put everything in the context of images. And so with sensors, with imaging sensors, every imaging sensor that I'm aware of images on a regular grid, a regular rectangular array of pixels. And so the sampling interval of the sensor is the same as its pixel resolution in the image. Right? So if you have a 10 megapixel, let's say you have a 9 megapixel camera with a square imaging sensor. And so then it's 3,000 by 3,000 pixels, give you 9 million pixels. Pixels are evenly spaced. And so then your sampling interval in space is related to how far away the image is, right? Because if you have 3,000 by 3,000 pixels, the actual size of the pixel depends on how far away the projected object is, right? The further away you're focusing on, the larger each of those pixels is in area. But the critical thing here is that they're regular, and the sampling interval of the sensor is fixed. Now, you can make that sampling interval increase either by zooming in or just walking closer to what you're imaging. And then the area of each pixel will be smaller. The angular field of view of the pixel will be the same. But by getting closer to the target or zooming in on the target with a variable lens, you effectively increase the resolution of the sensor. So sensors image with a single spatial frequency. And so we have to, when we're using it to make images, we have to accommodate that either by zooming in or zooming out or just getting closer to the target. But the important thing is that it's periodic. The pixels are a regular fixed spacing. And so what can happen with images is you get what we call constructive and destructive interference. And so again, we use sinusoids to illustrate that. If you have two sinusoids of the same frequency, or equivalently the same period. And they go like this. If you add them together, the peaks cancel the troughs cancel the peaks. That's destructive interference, right, where they cancel each other out. But if you have two that are like this, if the peaks and the troughs are aligned, then they add together. So they strengthen each other instead of cancel each other out. And so that's constructive interference. So when this happens with images, if the thing that you're imaging has a regular spatial pattern, and the sensor has a regular spatial sampling, then where the pixels align on the image, on the projected image, affects how they're recorded. And what can happen when you have periodic sampling of a periodic process, this constructive and destructive interference together can form what we call a Moiré pattern. And it appears as an optical illusion. So a simple example is if you have two sets of parallel lines and the spacing is exactly the same, then if you align them together, so the lines are lined up with each other, then that's constructive interference, right? And then you just see what looks like one set of parallel lines because they're aligned with each other. But now if you take that set of parallel lines and you shift one relative to the other, then they're offset. And it still looks periodic because the lines are regular. But now the spaces between the lines are wrong. They appear to be shorter than they are. So if you take the same thing, and instead of shifting the lines, you rotate one set of parallel lines compared to the other, you get this pattern. And so you see you get this kind of elongate diamond-shaped pattern. And so the dark areas overlap to form a completely dark area here. And the open areas, the gray areas, don't form a completely open gray area here, the maximum gray area here. And the result is this banding. So here's an actual example of a bird's feather. You've seen bird feathers close up. They're these parallel filaments that are grown together. And so there's a natural banding to the bird's feather structure. And there's a natural grid sampling of the sensor. And you're getting the same thing here. These banding features that you see, they're not really there. They're not part of the feather. They're a result of the regular structure of the feather combining or being aliased by the regular sampling of the sensor grid. Does that make sense? So the dead result, this is the aliasing, is this other secondary banding in the feathers. It's not actually there. It's just a result of the way the measurement was made. All right. Here's a more extreme example. I don't know if you can see this where you are, but this is a brick wall. So the structure of the wall is regular because all the bricks are the same size and they're all the same amount of mortar. And if it's properly sampled, you just see the regular spatial pattern of the bricks. But if it's aliased, if the size of the pixel starts to get close to the size of the bricks, then some of the bricks are going to be imaged properly and others aren't. But the pattern between the ones that are imaged properly and the ones that aren't will have a regular pattern repeating to it. And the result is you get what look like folds, like waves in the brick wall. That's aliasing. That's spatial aliasing. And you can see what makes it so dangerous, especially in this case, right? Because this really looks like waves in the brick wall, doesn't it? So if you're imaging walls for quality control or something, and you think that the brick wall has waves in it, and it doesn't, then you can imagine that. So the point here is, what's worse than what we call incoherent noise, noise that just looks like noise that doesn't appear to be information. That's bad. What's worse is what we call coherent or correlated noise. Noise that appears to be information is more dangerous. Because if you interpret it as information, if it's incoherent noise, then we can just try and ignore it. Maybe it conceals something of interest, but usually we can just try and ignore it. But if it's coherent noise, then we mistake it for information. Then that's where real problems start to arise. And this is the reason why we care about aliasing. In space, in time, in wavelength, and which is why we care about the way the sampling is done. The sampling process is critical to avoid both unnecessary noise, but especially coherent noise or correlated noise, noise that can be mistaken for a signal. This is another example of the same thing, moire pattern. This was I couldn't even begin to guess the word in Portuguese. The type of the cloth that you hang in front of the window, but the one that you can kind of see through a little bit. It's not completely opaque.
It's curtain in English.
It's what?
What's the name in English?
We would call these sheer. Sheer because you can kind of see through it.
Talvez persiana,
So it's not a commonly used word in any case, right?
Sure.
Okay. Sheer in English, the name for anything like this you can sort of see through, but not perfectly, we would call sheer, like stockings. Types of window treatments where you want some light to come through, but not all of it. We would say that that's sheer. If you can't see anything through it, it blocks all the light, then we call them curtains. Curtains are just there to block light or prevent people from seeing. But these kinds of things are sheer. And you can see, so you see the patterns in here, the waves, and that's just, if you just look at these, if you look at the actual thing, you don't see that. Because our eye brain sees continuously. But the digital sensor has discrete pixels, and so it appears, we get the sampling from.
It's a kind of veil.
Yeah, the veil is an example also. Yeah, and in fact, you can use it as a verb also. You can say that the sheer veils the outside view. Yeah, so that's, so what's the word for veil in Portuguese? Veil. I wish there were more of those. Okay, so this is the same idea applied to sampling in time. I'm not going to bother to read all of this now. You'll all have these slides later, so you can go back and read this if you want. There's an example of visual aliasing on this webpage, the temporal aliasing in a visual way. There's a demonstration on this webpage that's worth looking at. Okay, and pixels. When a sensor of any type makes an image, the smallest unit of light, of radiation that it can capture, is what we call a pixel. And or it appears as a pixel when you look at the image. And it's supposed to mean picture element originally. And so when a sensor creates an image, the smallest, what we call instantaneous field of view, that becomes the pixel. The smallest that the sensor has, everything in that field of view is averaged together into one measurement. And you're familiar with this when you look at images, right? There's a limit as to the detail of any image, and if you zoom in more and more, eventually you just see rectangles of solid color. And the brightness, or the color of each pixel, is a spatial average of everything in that area that is reflecting light back to the sensor. And so all the information of the different colors of light that were being reflected, all of that is lost, and what you get is one average color for that pixel. And so this is a figure from an old remote sensing paper that from the 1980s, I think, that was reminding people that when you look at an image, there's always more detail below the scale of the pixel that you're seeing. But some people have a tendency when they look at an image to think of each pixel as being homogeneous, with only one thing. And so the cartoon here shows an image of, I guess, a farm. And so what you have are little pixel cows, pixel river, a pixel house, a pixel tractor. I don't know what those are. And so the title of this paper was The Pixel, the Snare and a Delusion. Snare is a type of trap. Delusion is delusions. So the point of the paper was to try to remind people that you should never forget that there's always more detail below the level of the pixel of whatever sensor you're looking at. So now this graphic illustrates the effect of spatial resolution, pixel resolution, and it's not really spectral resolution, it's what we call bandwidth. Well, actually, no, I take that back. This is a form of spectral resolution. So spatial resolution has to do with the number of pixels in the image. Okay? As the pixels become larger, the spatial resolution becomes lower because it resolves less, and the spatial detail is lost. What's happening here is, as you go across, we're reducing the spectral resolution by reducing the number of gray levels that are represented. And so here, with 32 brightnesses of gray and 64 by 64 pixels, you can clearly recognize not only that it's a human face or human head, you probably even recognize whose head it is, because the person's kind of well known and has this iconic facial structure. And so we can see here the effect of reducing the spatial resolution, reducing the spectral resolution, or the gray number of gray scales, and both at the same time. And so you notice an asymmetry here about the diagonal in the information loss. We can give up a lot more detail in terms of gray levels, and still, I mean, even with only black and white, you can still probably represent the climate control.
Yes.
Okay. So even with only two gray shades, black and white, you might still be able to recognize not only that it's a person's head, but maybe even who it is. And certainly here, with 4 brightness levels, easily recognize it is. But in part, that's a consequence of our eye-brain system and the fact that this is a recognizable feature. you recognize this person because you know who it is ahead of time. You've seen many pictures of them before. But notice what happens as you go down in spatial resolution. I mean, you might still recognize that as a human head. That, not necessarily. Certainly not in either of these two. So, when you're dealing with sensors, this is an important trade-off. Because more pixels and more grayscale are both expensive. And so you can decide, especially if you're capturing a lot of images through time, right? Then storage can become expensive really fast. And so you can decide, you can often decide, you can configure the sensor before you start making measurements. With cameras, you can control the number of megapixels. You can control the averaging that it does, therefore control the amount of detail and how many images you can store before your storage device fills up. You can't generally control this with a normal camera. You can't generally control the gray shade with a normal camera, but with most instruments, most other types of instrument, you can. So you can decide basically how many bits of storage you want to allocate to each pixel. The more bits you allocate, the more different levels, brightness levels you can store. Okay, tomorrow when we start talking about remote sensing and image processing, I'll talk a little bit about the way that images and numbers are stored by computers and how knowing even a little bit about that can help you decide the best way to save data so that you don't fill up your device too fast. Okay, here's an example of pretty much the same thing, same idea, using different spatial resolutions of satellite imagery. So this is what Manhattan, central Manhattan, part of New Jersey, Bronx, Queens. This is what part of New York City looks like at 30-meter resolution from the Landsat sensor. This is false color composite, so 3 spectral bands, 3 different wavelengths. There's red, green, and blue. And this is 1,000 by 1,000 pixels at 30-meter resolution. If you zoom in and look at this more closely, this area up here, this is the campus of the university where I work. This is a park. This is another park. So you can see the overall structure of the geography of part of the city. You can see the larger features like the larger parks, the reservoir in Central Park, but you can't make out individual buildings, not at 30 meters. Buildings just aren't large enough. And so almost all of these pixels, the area the sensor is imaging for almost all of these pixels, it's seeing many different things. It's seeing some part of the building, some street, some sidewalk, some trees. And so when it averages all these together, the average color doesn't really mean much by itself. I mean, here you can see where the parks are because there's more green. You can see that there are baseball diamonds down here because there's sand or different color. You can see the campus has a fair amount of green on it. But you can't make out the individual buildings. You can't make out the cross streets, although you can maybe see some of the uptown, downtown avenue structure, maybe, if you know what's there. This is the same thing. This is the panchromatic sensor that Landsat 7 and 8 carry. It images at 15-meter resolution, but it only sees the average brightness in the visible and near infrared. So you don't have any color information here, but your pixels are half the size. And so now you can start to make out the uptown, downtown avenues. The avenues are wider. You can't see the individual, most of the cross streets you can't resolve. That one maybe, there's maybe a couple that you can see, but It's much easier to see the structure going this direction than this direction. Right? And that's the difference. That's because most of the avenues are about 15 meters wide or more, but the streets are narrow. And so the streets are getting averaged away, but the avenues appear as more coherent dark bands. Again, if you blow the pixels up, the same thing in more detail, you can see there. But you're still not resolving individual buildings. Now, if we use a different sensor, in this case the iconic sensor, has 4 meter pixels. It doesn't have as many spectral bands as Landsat, but the pixel resolution is quite a bit smaller. And now you can easily see individual buildings clearly. And of course the cross streets and the avenues. It also has what's called a panchromatic sensor that averages all the colors together and just shows the overall brightness. And here, its panchromatic sensor has 1 meter resolution. And so now, this area here, the center of the campus, now you can clearly see the dome on the main building. You can see the stairs, you can see the different facets on the roofs of some of the buildings. You can see different buildings roofed with different materials because of very different brightness. You can't quite see people at this resolution. If you went a little bit higher, you wouldn't see people, but what you would see is their shadows. So think about the geometry, right? The sensor is looking more or less straight down. Most people are not that big looking straight down, but if you look sideways, you see a different angle. The satellite, you can't look sideways, but when the illumination changes, and the sun's coming from a lower angle, the shadows get longer, and the satellite can see the shadows, the sensor can see the shadows. So what we often do, because this is very common, especially for the commercial sensors that collect the images that you see in Google Earth, most of those sensors are designed to have both color, image with color, and grayscale, but at different resolutions. And so what you can do is you can take the 1 meter brightness information and you can fuse it, you can combine it with the 4 meter color information so that you have 1 meter pixels but with color. The color doesn't have the same resolution, but you can make an image that's easier to interpret because it has the detail of this image with the color information of this image. That's called pan sharpening, and it's pretty easy to do. Part of the reason I'm mentioning it is that if you buy this commercial imagery, if you need to use it for research, then you don't want to use what's on Google Earth because that's not only is that not all the information, that's not even most of the information. Most importantly, the Google Earth images don't show you any of the infrared information. So if you're going to use it for research, you'll want to purchase it from the companies that collect it. And so when you purchase this imagery from these companies, they offer services to do some of the processing for you. So one important thing is that you want it orthorectified. You want it geocoded so that it's put in the right place, so that the geographic locations of the pixels are accurate. That's worth paying for, because otherwise it's very difficult to use if you don't know exactly where the pixels are. But they also offer this pan sharpening option of fusing together the 4 meter color with the 1 meter panchromatic, or actually the newer sensors will have 2 meter color and 50 centimeter panchromatic. They'll do this fusion process for you, and they'll charge you a few $1,000s for it. But you can do it yourself on the ND software on these machines in 15 minutes maybe. So if you think about a few $1,000s for 15 minutes to do it, and if you do it yourself, you can tune it to get it the way you like it visually. Because if you pay them to do it, they do it once and you get what you get. So spending a few minutes learning how pan sharpening works can possibly save you thousands of dollars at some point in the future. So, okay, all of these same ideas apply in wavelength as well as in space and time. And we'll go into this in more detail tomorrow, but let's start with this plot. What you're looking at here are reflectance curves measured for different types of vegetation by a sensor carried in an aircraft. It's what we call a hyperspectral sensor, meaning it oversamples. Hyper, the prefix hyper in, I guess, Greek means over, excessive. Hypo means not enough. And so when we talk about hyperspectral sensor, it means the sensor samples the reflectance in wavelength at many very small intervals, enough to capture the important details in this. These are called spectra. And what this is, it's a measurement of the fraction of the light that's illuminating something. The fraction of that illuminating light that's reflected off back to the sensor. So it's a fraction, it's between 0 and 1. If something's perfectly reflected, it reflects every bit of the light, it has a reflectance of 1. Almost nothing has a reflectance of 1. There are some synthetic materials, but in nature, about the brightest thing you see in nature is fresh snow. And fresh snow only gets up to about 85% reflected. Almost everything absorbs some light. But the amount of light it absorbs depends on the wavelength of the light. And so different materials absorb different amounts of light at different wavelengths. And that difference with wavelength tells us something about the chemical composition or the structural composition of the thing that's being illuminated. This is why we care about, this is why we have hyperspectral sensors, why we care about this, is because you can distinguish different materials by the amount of light they absorb or reflect at different wavelengths. In fact, this is the reason that our eyes, this is why our eyes detect different colors. Our eyes are basically integrating over the visible wavelengths, just these here. And what we perceive as color is really just a function of the reflectance of the objects and the color of the light that's illuminating. And so what you see here for vegetation, this is the visible wavelengths that our eyes are sensitive to are just 0.4 to 0.7 microns here. This is all infrared. Our eyes don't see any of this. And so what we have here are 4 different types of live vegetation, and blue in this is some dead grass. And what you see is that all of these curves, except for the blue, they're different, but they have some features in common, right? They have some similarities. One big similarity is that they all have very low reflectance in the visible. Anybody know why? So this is the characteristic of vegetation, is that it absorbs almost all the light that's incident on it in the visible part of the spectrum. But then, as soon as our eyes lose sensitivity at 0.7 microns wavelength, vegetation becomes very, very reflective. Up to, this is about 0.7 reflected. The grass in the near infrared here is reflecting about 70% of the light that's shining. And so vegetation absorbs the light so much here because of chlorophylls. Chlorophylls are pigments and chemicals in the leaves. You know chlorophyll? So it's chemicals in the leaves that absorb sunlight and use it for energy to drive the plant's processes. And And so there are two different types of chlorophyll. One absorbs mostly visible red, the other absorbs mostly visible blue. That's why the reflectance is so low here. The reason vegetation appears green to us is because it's a bit less, between the two chlorophylls, there's a bit higher reflectance, lower absorption. And so the shapes of these curves here determine the shade of green that the leaves appear. But the thing they all have in common is they all become very bright, very fast, right at the same wavelength where our eyes are not sensitive. Why might that be? What evolved first, plants or humans? Plants were around before humans were for a while, right? And all plants use use chlorophylls to absorb sunlight, derive energy from sunlight. And the probable reason that, well, we know that this is called the red edge, this really sharp increase in reflectance at the very longest wavelength of red that our eyes see. And so plants are all pretty reflective in the infrared, very absorptive here. They're absorptive here because the chlorophylls evolved to absorb sunlight and convert it to other types of energy. Plants are probably reflective here because the chlorophylls can't absorb energy at these wavelengths. So the plant leaves reflect energy at these wavelengths. They don't want to absorb it if they can't use it. Why would a plant not want its leaves to absorb energy that it couldn't use? What happens to the energy when it's absorbed? It had to be. Right, and you can't, energy is not created or destroyed. And so if you absorb energy in the form of visible light, something has to go somewhere, right? What happens when you stand in the sun? Especially if you have dark hair and no hat. Right? Your head starts to heat up. The same thing will happen with leaves, right? If they absorb energy and they're not using it for anything, it turns into heat. And plant leaves are full of water, right? So if the plant's leaves get too hot, the water is going to want to evaporate out of it. Bad news for the plant. And so this is very likely an evolutionary adaptation. Plants, this is the part of the plant leaves that reflect the sunlight. It's called mesotome. This is probably an evolutionary adaptation for the plant to reflect the wavelengths of light that it can't use to drive photosynthesis. Probably. And so out here, you see these other dips. Is there any place the reflectance goes down, we call it absorption, or an absorption band, or an absorption feature, because it's showing where the wavelengths, where the compound absorbs light. So, in addition, all plants have a big absorption here, about 1.4 microns, and another one here, about 1.9. These two absorptions are due to liquid water. Water absorbs at all infrared wavelengths, but most strongly at these two wavelengths. And so the water in the plant leaves is absorbing the energy of those wavelengths. And so the plant leaves reflect more energy in between at these wavelengths. The sensors can detect that. So the gray bands here are the wavelengths where the Landsat bands are sensitive. And so if Landsat had bands at 1.9 and 1.4 microns, then you might be able to use them to see how much water was in the plant's leaves. And in fact, there are sensors, handheld sensors that we carry, you can get that farmers use, especially, that will measure light at all of these wavelengths. And they can use these and point it at a plant and look at how absorptive or reflective it is in these wavelengths and tell how much leaf water the plant has. So you can use it to detect water stress in plant roots. But the Landsat sensor doesn't have bands there. It's not sensitive to these wavelengths. Any idea why? I mean, if we could measure leaf water content in plants from space, that would change agriculture, right? Certainly irrigation. You can see where the plants need, seriously, right? You can see where the plants need, where you need to irrigate more and where less.
Probably because we don't want to see the amount of water in the rest of while the satellite is orbiting the Earth, it would be over receiving a lot of information that we don't want to receive.
Right. So, did you all get that? So the problem is that it's not just the water in the plant's leaves that it would see the absorption from, but the atmosphere, right? And you're looking down through, depending on where you consider the atmosphere to start, at least 100 kilometers. Most of the water is in the lower atmosphere. And so for a satellite to see it, the sensors in the satellites are 600-700 kilometers above the Earth's surface. And so they have to look through the atmosphere. And so the water vapor in the atmosphere, even though it's not much per unit volume, if you have to look through hundreds of kilometers of atmosphere, the absorption of the water vapor in the atmosphere is going to absorb the sunlight. You wouldn't be able to see the difference on the ground because the atmosphere itself, you'd be seeing the atmosphere. And it absorbs it so deeply that almost no energy would be able to get in or out through the atmosphere of those wavelengths. So these measurements were made with this sensor. This is a NASA instrument called AVERIS. We'll talk about this a bit more tomorrow. It's an imaging spectrometer that measures not just these six wavelengths, but it measures 224 wavelengths, very narrow intervals. And with the sensor, it's flown in an aircraft. And with the sensor, they're able to get these kind of measurements for the same reason that they're able to see this very fine spatial detail, different lanes of the highway, individual houses. Because the aircraft is flying much lower than satellites do. And so the sensor on board the aircraft is only looking through a few hundred meters of atmosphere, not hundreds of kilometers of atmosphere. And so by flying closer to the target, less atmosphere, they can actually image the leaf water content because there's not enough water in the atmosphere at that low altitude. They're close enough to it that it doesn't absorb all the wavelengths. So why are we talking about this with respect to aliasing after all this? Because the Landsat sensor, it's only one measurement for each of these gray bands. It measures only 6 different wavelengths, and it averages over the range of wavelengths shown in gray. And so these spectra collected by Landsat would be just 6 points connected by straight lines. No idea what's happening in here, in here. And so the Landsat sensor can't see features like this, not only water absorption, but this other feature here. You notice the dead grass has an absorption there that you don't see in the other ones. All these details, these little bumps here, that's all information. Potentially useful information that may, in some cases, even allow you to discriminate between different species of trees. So, the hyperspectral sensor is oversampling the spectrum. It's oversampling the absorptions. It can resolve features like this because it's sampling more frequently and in narrower intervals. That makes sense? It's a lot to digest, right? We'll talk about this kind of thing in more detail tomorrow, but this is just an example of the difference between oversampling, reflecting spectrum, and undersampling. So what you're looking at here, this is what we call a hyperspectral cube. So the front face of the cube are individual pixels. So you're seeing geographic space here, distance in X and Y. And what you see here are the two sides of the cube. This is just the reflectance versus wavelength, going from short to long, just like that. The warmer colors are higher reflectance. And so you're seeing just the pixels along the edges. Just this row of pixels and this column of pixels. Now you're looking, sort of looking into the wavelength dimension of the cube. And so now you can see, for this whole row of pixels, you can see how the shape of the red edge changes, for instance. You can see a little bit of difference in the ortho absorptions and the visible. But mainly you're seeing the differences in the bright part of the near infrared. And so this kind of thing, this give you a way of mapping the tree species, for instance. And not just along this line, you can see the variation along the line here. But knowing about these differences, you can map each pixel. If you can distinguish a consistent difference in the reflectance at some wavelength, then you can use that to map the composition of each pixel in the image. Okay, I'm not going to ask if everybody gets that. I know that's a lot to absorb today. We'll talk about this stuff in more detail tomorrow, more slowly, but this is what a lot of sequence, because when I teach remote sensing, I talk about all of that before I get to this slide. So. Okay. I imagine you're going to be relieved to hear me tell you that I'm not going to talk about this in detail right now. In part because I've already talked about the ideas of means and dispersions. In part because I think a lot of you have probably already seen this before. And in part because you can read this on your own if you want to more effectively than I can try and explain it. These are just the formulas that we use to represent these statistics. The statistics are used to try and represent the characteristics of large numbers of numbers, and some alternative statistics that you can use, which all of this you can read on your own, so I won't do that. I think I talked about most of this already also. Normally, when you see a distribution of points shown in a textbook, an illustration, almost always it looks like this. Has this shape, usually. Any idea why? So this is what we call in English, we call this a normal distribution, or sometimes a Gaussian distribution after the person who popularized it. I think part of the reason is because it's nice, it's symmetric looking, it's simple, it's smooth, it has only one bump. It's a nice idealized representation of the distribution. But the other reason is, and the reason that normal distributions are so popular is because they're very, very common in nature. A surprising number of real distributions of things are very well described by this shape, this normal distribution shape. Does anybody know why? This is a bit more advanced than
It's the variance, like in the true value. I know it's common in nature.
There's something called the central limit theorem, and it's a theorem that was developed and proven mathematically, but it actually holds up in nature. And I'm going to oversimplify it, but basically what it says is that if you take a number of other distributions that are not normal like this, you know, distributions that are what we call skewed like this, that are not symmetric, and distributions with different means and different dispersions, different widths. If you take samples from processes that come from these different distributions, mix them all together, they'll generally converge on a normal distribution. So if you mix other things together, the result is usually a distribution that looks like this, that has this shape. And it seems kind of unbelievable until you've seen it proven. But seeing it proven takes about 40 minutes if you have some statistics background. I've never seen a faster demonstration of it. But if you've seen it proven mathematically, it's pretty impressive. But the thing is that you can simulate it yourself just by taking different types of measurements and mixing them together and looking what the result looks like. And it's really, really amazing how often you'll get something that matches this shape. Really, and the general shape, right? So the mean value will be different, and the width of the thing will be different. But it's really incredible how often you can take all sorts of measurements that you think have nothing to do with each other, mix them all together, and the resulting histogram that you get can be described really well with this shape. The magic of statistics. Anyway, so as you know, the mean is the single representative value. It's the value that's represents the largest numbers of observations, the peak of the mode of the histogram. The dispersion, or the variance of the standard deviation, represent how wide it is, how much it varies from its mean. And then there's a more general type of distribution called the log normal that can become a normal distribution under certain conditions, but it's a more general in that it can describe distributions that are not symmetric. And between the normal and the log normal distributions, that's most of the distributions that you find in nature. Well, no, I think that's not correct. That is an even larger fraction of the types of distributions that you find in nature. And the reason that we're talking about this now is not because I like standing here talking about distributions. It's because the idea of these distributions and the dispersion of the distribution and the shape of the distribution is central to the tool that we're going to use later to do the spatiotemporal analysis. So you can think of it as the price that you have to pay to understand how that tool works and be able to get all the savings of time and money that the tool will provide is you need to spend a little bit of time thinking about distributions and sampling and things like that. But if you're going to be working with spatiotemporal processes, I assume you wouldn't be here if you weren't. If you're going to be working with spatiotemporal processes, this is a bargain. This is a very small price to pay for a tool that will enable you to do things that seem unbelievable to the beginning. So that's the reason I'm doing this, but I'm not going to stand here and talk about it any longer than necessary, because you can look at these graphics on your own. And if you have any questions about any of this, I'm happy to answer it. I don't want to stand here talking about it any longer than necessary. Okay, so that is it for the lecture part.